We always get a positive response when we make compilations, so here's a big one for you. In this massive compilation, I've put together almost every video that we've made thus far that covers Victoria's geology, mineralogy, and some geological exploration that was done to answer some unsolved questions of mine. We'll cover everything from supervolcanoes to orogenies, continent-to-continent collisions, earthquakes, significant gold deposits, and the recent wave of volcanism. Now, some of these videos are a tad older when I had a low quality mic, and I tried to put these ones at the end. But the narration is still understandable, and the topics are still important enough for me to feel compelled to include them in this documentary mega-series. I'll be covering a lot more content focused on interstate and overseas regions now that I have some free time to do so after hiring some help. I've already started working on the scripts, and I've been catching up on my knowledge of the geology of each region. This morning I released a comprehensive article on the geology of the Northern Territory on my website, and you can find that at www.ozgeographics.com under Ozgeographics articles. So without further ado, let's get into the many fascinating stories we've covered regarding Victoria's past. This land is super flat, obviously, but if we were to dig about 150 feet beneath here, or 46 metres, we would discover the remains of a completely different landscape, a much more ancient one, which once existed on the surface level, dominating the land here, and it did so for well over 400 million years, before it only just became covered up in this specific area within the past few million years, after a new wave of volcanism began in Australia, which would go on to release voluminous amounts of fast-flowing lava that solidified into the rock known as basalt when it cooled. Before it solidified, though, these lava flows poured into the nearby ravines and river systems near to the many thousands of volcanic vents that were ultimately responsible for its release. And it would very perfectly mould into the shape of the river, building up the depressed waterway and diverting future flows. And the lava flows themselves could travel for many kilometres before finally coming to a rest, allowing it to cover vast distances within a river in a single eruption. And the result of this? The entire inland watercourse in central and western Victoria has been altered. The literal arteries of the land have been covered over, and new ones have been forced to take its place, so to speak. And this is evidenced by the rocks in this weird hill here. And this weird looking hill has a fascinating origin story behind it, and we're going to cover that in this video. This hill-like stack of debris and sedimentary rubble is known as a deep-lead mullock heap, and it sticks out like a sore thumb amongst an otherwise flat land. But what is it, you ask? Well, all of the material that you see here was pulled out of the aforementioned ancient and now buried landscape that I just spoke of by hand by miners who dug deep shafts in an attempt to intersect the primordial rivers and tributaries that once flowed through here, which were now lying buried beneath the many layers of differing lava flows that were recently extruded here. Some areas were covered deep, and others were more shallow. These lava flows would be erupted en masse, and they would flow, and eventually solidify, in thin veneers, slowly building areas up, over time, layer by layer. You can find many of these protruding and strange hill-like shapes pretty much everywhere in areas of Victoria that have the occurrence of buried gold-rich paleo rivers, which is the correct term to describe this kind of ancient river system. But in Victoria, we call them deep leads, and deep leads play a big part in our state's history. I'm fascinated by deep leads, and I don't really know why. It's not so much the massive yields of gold associated with them. It's something to do with, things that are ancient. Like, I spend 1% of my time actually imagining the gold and nuggets contained within them, and 99% of my time just wondering how Victoria looked prior to it being covered over by these lava flows. And something about that intrigues me so much that it's a borderline obsession at this point. Now, it's safe to say that this kind of mining absolutely sucked. Like, wow, it was horrible. But it was well worth it for the riches that lay within these primordial waterways. And I love coming to these mullock heaps because they exist within land that is very clearly flattened, and is therefore dominated by recently extruded volcanic material. But the fact that these piles exist both offer an insight and prove that these ancient rivers even exist at all to begin with, in case someone was, for whatever reason, skeptical. But they can also show us the direction that whatever ancient river these miners were chasing once flowed, when multiple of these massive deep-lead heaps can be lined up in a distance and seen by the naked eye, which I think is pretty cool. So the pile of sedimentary rocks that you see here were pre-7 million years ago at what was then the surface level of Victoria, where they were pulled out from the now deep ground alongside the much sought after river gravels, which were worn down and rounded from thousands of years of river action, within which precious gold could be found, en masse, snugly lying within a matrix of material that was dominated by the many cobbles of river rocks that existed alongside quartz boulders of varying sizes, from small to exceptionally large. But the mine that left this mullic heap here pulled it from a depth of between 100 to 200 feet, or 30 to 60 meters. And this is actually pretty shallow, amazingly enough, compared to many other places that would have to dig 200 or 300 feet, or 60 to 91 meters or more, to get the job done. So there was once a completely different river system that snaked its way through whatever land ancient Victoria existed as. And the arteries of it can be clearly seen by tracing the deep lead workings that occurred here, and that were marked by the Geological Survey of Victoria. Though spotty, when you follow these lines you can see that the river system prior to the present day Yarrowee River in Ballarat, which in present day flows south, once flowed north, where it zigzagged its way through hundreds of kilometres before finally reaching the Murray River. It did so when the topography here was 50 to 60 metres lower than what it became after these lava flows filled up the ancient ravines that dominated this once rugged and far more mountainous land. But in present day, the Yarrowee, which took over as the dominant waterway here after the recent lava flows buried the rivers that preceded it, now flows out towards Geelong, and this is obviously a major shift. For millions of years, the waterways of Western Victoria remained largely intact and unchanged, owing to the fact that it became pretty geologically stable after the 300 million year mark. At least it did in this part of the land. In fact, it might well be speculated that for well over 300 million years, this had more or less been the pathway that this river system took, showing you why these deep leads were so bountiful and saturated in precious metals, and why they contained more gold than the recently constructed alluvial water bodies that took over post-volcanism. But there's another thing worth stating that will be particularly interesting for anyone who's from Victoria and who lives in this area, around the Central Highlands or in the volcanic plains to the west of Melbourne. And that's the fact that this area was, at least before the recent lava flows, 30 to 50 metres lower than what it currently is. Imagine viewing Black Hill, but from 50 metres lower. Imagine how different Ballarat would look if the western parts of it were 50 metres lower. How everything would look. Especially the mountains, both in Alluvial National Park and to the west of it. They'd be striking. I mean, they already are. But if they were 30 to 50 metres taller, they'd be monsters in comparison to their present day appearance. And this is how they stood for almost all of our history, until those damn pesky volcanoes reared their molten heads and changed the land. At least until erosion finally does its thing and reverses their impact. Hurry up, erosion, you son of a bitch. So this is the story of only one of many of the deep lead heaps that exist in Victoria. I know that recently a lot of content has been centred around the Ballarat district, and they have been for a good reason, as I attempted to get as much footage of the area as possible before making my recent move. After this wave of videos, expect episodes to be centred around Eastern Victoria and Melbourne, as the next journey of discovery begins, and as I attempt to answer some burning questions that I've had for years, whilst simultaneously heading back to the city that I grew up in after spending years out in the bush, staring at rocks. Thanks for watching. And that isn't a joke. I was staring at rocks. I love staring at rocks, man. Rocks are awesome. Australia is an incredibly resource-rich country, with bountiful amounts of gold, silver, copper, iron, rare earth elements, platinum group metals, and the best damn opals you can find on our planet, and this is to name only a few of our noteworthy resources, because in reality we basically have it all. But even though we are one of the largest iron exporters in the world, that iron is coming from the exceptionally ancient land of Western Australia, and is actually a completely different form of iron ore to the one we're going to cover in this video, in that it's far more pure, and the type of process that formed the ore body to begin with actually no longer exists. But iron in Eastern Australia? Well, that's a different story, because it's the youngest part of Australia, with it being little more than a deep ocean 500 million years ago. So where did this iron come from then? We're going to attempt to answer that question in this video, and we're also going to take a closer look at this site and discover why its existence is so strange and so unique to begin with in this part of Australia. So I'm here in an area known as Lal Lal in Victoria, Australia, and this is the only iron mine to have ever been attempted in Victoria. And for a good reason, as economically viable iron deposits really don't exist here. But the fact that we can find it here means they're the kind of iron deposits that aren't exactly high quality, to say the least. And why is this? Well, because it produced pig iron, which is the name given to a crude form of iron that contains the highest amount of impurities, and is therefore the cheapest as a result. The fact that this iron mine was even attempted to begin with is quite incredible, honestly, but there was a logical reason for its formation. The gold rush that occurred here in the mid to late 1800s saw the need for lots of iron for a magnitude of differing reasons, from railway construction to machinery and more. And even though pig iron was crude and impure, it was more than suitable to do the job. But even with this, the mine didn't last long. Within a decade, the company went bust, with the mine opening in 1875 and closing in 1884, and any further attempts to reopen it in the future would prove unsuccessful. This mine also had a smelting works on site, but in present day, not so much is left apart from the insanely large chimney that they built here. But I gotta admit, it must have been fun being the miner who was responsible for heading downhill, as they would fly down it along with a minecart that was filled with iron ore, in order to unload it before making the journey uphill again. Now, as you can see, this chimney hangs pretty precariously, and probably doesn't have many decades left. The entire chimney was actually once wrapped in an external layer, that unfortunately no longer exists. And there used to be a bridge that connected to the top of it as well. And look at those massive iron-rich rocks that they used to line it. Unbelievable stuff. Those rocks are actually the hard rock version of the ore that these guys were mining. During my studies into this operation, I couldn't find anything regarding what type of mine this was. Was it a hard rock one, meaning they pulled solid rock out, crushed it, and extracted the iron through smelting, or an alluvial one? But the moment I got here, it was obvious to me that this operation was most definitely an alluvial one, meaning they found an ancient waterway and they were mining the soil-like particles of iron that had eroded from the surrounding ore, which they readily scooped up by the shovelful and threw into the furnace, alongside some locally sourced limestone from a nearby ancient coral reef to use as a flux, and locally sourced charcoal, which was created by the mass felling of the old eucalyptus forests that stood here in abundance, much to my dismay. But I get it, you gotta do what you gotta do, and life in the 1880s was harsh and unforgiving, especially in Australia. But as you can see, they were chasing the curvature of an old stream. Rounded quartz exists here, but not much, meaning they mined this for gold and took much of the quartz along with any other cobbles before separating it from the gold. And this makes sense, as gold is what they were chasing to begin with, which more than likely led to this discovery of iron ore. The fact that this quartz is exceptionally rounded tells me that this was either a very long-lived stream or a major one. It seems to be the latter rather than the former, and you can see that the miners left the rocks on either side of the riverbank behind. And these are the rocks that the alluvial iron is eroding from. But why is iron here to begin with? Well, this is the fun part. The geological setting allowed for the decomposition and accumulation of anything that lived and died, along with anything that was eroded from here in the past 400 or so million years, since it was uplifted above dry land from the deep sea where it once lay. And this area has always existed as a kind of bowl shape topographically. Recent lava flows have offered quite a bit of infill, though, which obscures the real topographical nature that existed here throughout much of history, as this whole area was more or less one big dome shape from west to east, from here to here. And it still is, even with the recent wave of volcanism, which added some 50 meters or 164 feet worth of volcanic material in the form of lava flows. And the river systems here seem to have always run south. So in the past 7 million years, the land became dominated by volcanic eruptions, which released an immense amount of lava, building up and covering much of the ancient land that had more or less existed in the same state for the past 300 million years. And one way of gauging just how intense this really was is by looking at this big shelf of basalt over here. As you can see, this valley is cut very deep, and the land here is pretty damn steep as a result of that. But the lava flows that form that shelf used to reach all the way up to where I'm standing and above it when they were freshly released. The Moorabool River has cut through the basalt in time like a knife through butter, and after the basalt was eroded, it continued carving through the ancient sedimentary layers, forming this valley. Before this land was a dome in its shape though, we had sedimentary material that was deposited in a deep sea setting, the accumulation of which begun around 550 to 600 million years ago, with this sediment flowing east from the shorelines of the ancient supercontinent of Gondwana. The origin of these sediments occurred from rocks in South Australia and Antarctica, which was joined to Australia back then. These deep sea sediments would eventually become uplifted, beginning around 500 or so million years ago, and after multiple tectonic events, it would eventually be thrust out of the sea. One of these tectonic collisions was a continent-to-continent collision, an event that's known for creating pronounced mountain ranges, and for forming major intrusive batholith magma chambers, which bubble up and coalesce deep within the Earth. This collision was that of the microcontinent that Tasmania sat atop, and it collided with this part of Victoria. This collision led to the inevitable fusing of Tasmania with Victoria. To the west of here, we have the beginning of the Brownhill Ranges, which is marked by a major reverse fault, and is one of the many lines that mark the site of an ancient subduction zone. And these ranges mark the western extent of the dome. And to the east, we have another major fault, created when Tasmania collided with Western Victoria, which only served to further crumple and buckle the surrounding area, producing uplift and creating tremendous mountain ranges that once stretched high up into the sky. This iron mine is located just west of this major fault, and even though the land within the dome is mountainous, and was once a far taller and much more mightier mountain range, it had always been dwarfed by the mountains to its east and west, making this area more of a basin of sorts, even with it being mountainous, as surprising as that sounds. The dome-like structure of Lal Lal and the surrounding area really began 360 million years ago, following the collision with Tasmania. As the tectonics here began to settle down, massive waves of magma intruded into the crust in the final stages of this continent-to-continent collision, and this magma baked the sedimentary rocks that were on top of it, transforming the rocks into something known as a hornfels, which is a label given to a rock that has been metamorphosed as a result of high heat but low pressure being applied. And this type of thing occurs when rocks make contact with magma. So after this intrusion, 360 million years ago, the land more or less became geologically stable around the 300 million year mark, where it remained up until the recent volcanic eruptions that suffocated out the ancient landscape occurred. By this point, erosion had really worked the ancient mountain range that existed here down. So much so that the underlying, now solidified magma chamber, which is the guy we spoke of who intruded here 360 million years ago, became exposed to the surface. And in various areas, the highly weathered granodiorite and granite rocks that once churned within this deep magma chamber lie in plain sight. When we view this massive magma chamber on gravity, we can see the aforementioned dome-like shape. And geez, it was massive. This was a gigantic, almost circular magma chamber. And because it solidified beneath the earth rather than erupting, it's known as a batholith. This batholith was once located many kilometers beneath the surface of the earth when it was active, showing just how much erosion has occurred here over time. Now that we have the geological and geographical setting down, we can discuss how these iron deposits formed to begin with. Along with them exist deposits of brown coal, and both are linked in an indirect manner, as both of these deposits require a depositional environment for them to form to begin with. meaning both the brown coal in Lal Lal and the iron deposits require an area where material was allowed to sit and accumulate for them to form, as opposed to them being transported out by the waterways, like what would occur in a well-drained area. So this entire bowl shape was and still is an area of stagnation, meaning anoxic or oxygen-less conditions prevail. As you can see, the town of Lal Lal has areas of major lake deposits, showing water is still sitting here rather than leaving. So it's evident by these deposits that this area was one that was dominated by swampland, lakes, and subtropical to tropical rainforests throughout most of its history, as coal is the result of the partial decomposition of plant material that's subject to increased pressure and temperatures that occurs in an airless environment. Which essentially means things died, then more things died and covered up those things, then even more things died and covered up those things. And layer after layer of organic material gets built up over time, and the pressure inflicted upon the bottommost layers by that or by any tectonic element eventually turns this biological material into brown coal, but only if it's in an anoxic environment. So this area was definitely one that was dominated by swamplands. When this part of Australia was closer to the equator, this area became tropical, and as it drifted away, subtropical. And that was when much of the iron-rich limonite deposits were formed. Limonite is an iron ore that is actually a mixture of different iron oxides that have been weathered out of a host rock, and that accumulate as a result. Because iron has a heavy specific gravity, it tends to accumulate, and their heaviness makes them resistant to being transported out by water. And because its existence is one that's formed as a byproduct of something, that makes it a secondary material. The actual meaning of the word limonite in ancient Greek is wet meadow or marshy lake, and this is because limonite is also known as bog iron ore. And bog iron was a very important early form of iron ore that humans mined during the BC times. But the fact that it's associated with the many marshes that exist in Europe is where bog iron got its name, and it serves to further highlight the swampy anoxic conditions that prevailed here. This land is one that is more or less stuck in a dome-like shape, and this is what was necessary to form part of the limonite, aka the iron ore, which was derived from two sources. The first was from organisms known as iron bacteria, which convert ferric to soluble ferrous salts in conditions free of oxygen. The second is from the erosion of the very same quartz reefs that the miners were already chasing for gold. Only it came from the minerals within these reefs that were ignored, and in some cases despised, as pyrites, which is also known as fool's gold for the fact that it does look very much like gold does, thus its nickname, occurs in these veins. But it, along with other iron-bearing minerals, became oxidized and hydrated as erosion slowly worked to whittle the quartz reefs that they were contained within down over time, and these iron-bearing minerals would become deposited and would accumulate within these acidic swamplands and the stagnant, barely flowing streams. And in time, they would be turned into limonite deposits. Now, it's kind of been a goal of mine to accumulate and smelt some iron for years, so if you'd like to see a video with me attempting to do that, let me know by clicking the like button. I'll use some of the same alluvial material that these miners used. This deep red soil that's just saturated with iron. The soil itself is literally just rust. But yeah, limonite is basically a blanket term to describe an ore that's an accumulated deposit of many different iron-bearing minerals, and in general they're a combination of hematite, magnetite, and pyrites. These iron deposits are the result of both bacteria, alongside tens to hundreds of millions of years worth of erosion that occurred in a basin-like topographical area which allowed for the accumulation of virtually anything that died and anything that weathered or eroded. A truly fascinating origin story. These iron deposits aren't really valued today, but during the Iron Age, around 1200 BC, our ancestors would have absolutely killed to have had access to this, and we know that for a fact. Damn murderous humans. So this is the story of the iron deposits in Lal Lal. Now these aren't unique, and I've seen many areas in Victoria that were saturated with similar looking iron deposits. But this was the only place where this type of endeavour was ever attempted, and it's looking like it's going to stay that way for a very long time. Thanks for watching. There's a beautiful site just east of Ballarat known as Gong Gong Reservoir. This picturesque and highly manicured garden displays an interesting interplay of volcanism, which highlights the many iterations this ancient land has undergone throughout the vast recesses of time. And we're going to nerd out on what these rocks tell us and the epic story that follows. Welcome to Oz Geographics. This cutting here shows the ancient 360 million year old granodiorite and quartz monzonite that was once located within an active and churning magma chamber deep beneath the earth. And the last time it was alive in its magmatic state was during the late Devonian period, meaning this body of magma, which stretches for a massive distance beneath the land, with it outcropping in various places here and there, penetrated the crust at a time far before the age of the dinosaurs. And placed neatly on top of it is the most recent basaltic lava flows that buried vast swathes of land, covering almost 1/3 of the entire state of Victoria beneath basaltic rock that could be 60 meters or more in its depth. This beautiful interplay shows how dynamic this land once was, and still is, with ancient intrusives and more younger extrusives in full display, hugging one another in a strange embrace. When it was decided that this area would be made into a reservoir, some 160 odd years ago, the inception of the beautiful gardens that you see here began. As you can see, the rocks here were all quarried to make the beautiful pathways and garden beds, with basalt, granodiorite, and quartz monzonite so beautifully interlain and carefully selected in its positioning. You can still see sections of the large rocks that were quarried by hand with a chisel bit by bit, and areas are designated for basalt and others for the quartz monzonite and granodiorite. So what do these rocks tell us? This granodiorite, as the name suggests, is a middle ground between granite and diorite. Whenever we see this rock, we know that an ancient subduction zone occurred here. The same goes for quartz monzonite. This name is probably very familiar to any geology nerds from the US, as the goldfields are dominated by these types of rocks, as a result of the active subduction zone occurring there. And this is a perfect model to explain what occurred here 360 million years ago. These rocks are commonly associated with volcanic arcs, especially in Cordilleran mountain building events. The Great Dividing Range straddles this region and is at its highest elevation in the area between Ballarat and Creswick. But the formation of it occurred long after this granodiorite and quartz monzonite was deposited here. Instead, if we look at the fault map, we can see the truth of its origin. It's right on the border of a major fault line. This fault line is the boundary of one of the many subduction events that occurred in Victoria. And similar to the Andes, this area was once a site of extreme chaos, as earthquakes and volcanism run rampant during the time of the Devonian, across much of the state of Victoria, from east to west. In this region, this line here shows us that an ancient oceanic plate dipped beneath the continental crust of ancient Victoria, meaning where I am right now was once the border between the dry land of Victoria to the west and the ancient Paleo-Pacific Ocean to the east. On the gravity map, we see something fantastic. This perfect rounded blue shape here is granodiorite and quartz monzonite. It stretches deep into the earth, and as you can tell, it takes up a massive area of land. Batholiths are massive magma chambers, formed by very large igneous intrusions that extend to an unknown depth into the Earth's crust. So even though this rock never had a chance to erupt, this land would have been one chaotic hellscape, with supervolcanoes and typical Plinian volcanoes existing at this time, pretty much en masse across the entire state. This time period was Victoria's most ferocious, at least in terms of the volcanism that was experienced here. And nothing has come close to the disastrous eruptions that occurred in this state at that point in time. If this magma had have erupted rather than solidify, the rock released would have been known as rhyodacite, which is the extrusive version of granodiorite. When this magma solidifies in the earth without erupting, it's known as an intrusive. If it erupts, the name becomes rhyodacite, and that is an extrusive, because it was extruded onto the earth. So these rocks are associated with some pretty intense and devastating explosive eruptions if they make it to the surface. But it never had a chance to do that. Instead, it cooled and solidified beneath the Earth 360 million years ago, only to eventually be exposed via erosion. As you can see, there's colour changes in the intrusive rocks here. Why? Because in a slowly cooling magma chamber, things begin to separate. Everything has a different melting point, and because of this, as the temperature cooled here, minerals began to separate and accumulate in different regions in the ever-cooling magma chamber, as crystallization occurred, leaving us with different mineral assemblages, and thus we have different coloured iterations of the same rock from the same magma chamber because of this. Then we have the recent basalt that was erupted en masse across the state beginning around 7 million years ago, transforming Victoria into the third largest volcanic plain to currently exist on our planet. These volcanoes penetrated through the crust as Australia passed over a magmatic hotspot. We've already made a video that addresses this topic, you can find a link to that in the description. And to this day, this region is still technically considered to be volcanically active, and it's very probable that more eruptions will occur in time, although they'll probably be situated much farther south or southwest from this current location, due to the positioning of the hotspot in present day, with Australia drifting north over it ever more. It's worth noting that if Victoria hadn't become recently faulted and stretched by the rift event between it and Antarctica, then it's very likely that the recent basaltic eruptions would have partially melted these intrusives, and would have released more explosive eruptions as a result. But because they rose with ease, their journey seems to have been one that was quick and easy. When viewed on magnetics, we can see exactly where these basaltic eruptions occurred from. And we can find the centres that release the lava, that would eventually flow over the ancient granodiorite and quartz monzonite. The lava flows here were intense. They occurred en masse and completely altered the land. They flowed over these intrusives, burying them for some time, before erosion eventually revealed the underlying intrusive rocks again. At least it did in this region. So here we have hundreds of millions of years of history staring right at us, that speak of how different and chaotic this land once was in the vast recesses of time. It's likely a volcanic arc once dominated here, and I'd be willing to bet that it still exists to some extent deep beneath the earth, but that's a subject for another video. Thanks for watching. The Permian-Triassic extinction occurred 250 million years ago, and is believed to be the most significant and profound extinction event since the origin of complex multicellular life. But along with this Armageddon occurred the beginnings of the separation of two landmasses that, before this, had been joined up for well over 300 million years. Those are Australia and Antarctica. They joined up during the formation of Gondwana. But the detachment of these two continents may have had an explosive catalyst. So, in this video, we're going to take a look at the relationship between the massive impact crater in Antarctica and the parting of it with Australia. Buried under 800 metres or 2,624 feet of ice lies a magnetic anomaly that has hinted at a possible bolide impact since the early 1960s, when the first magnetic images were made available to scientists. In 1976, the hypothesis was detailed in a paper, and the evidence cited included a sizable negative gravity anomaly, coincident with a subglacial topographical depression. The measurements were 243 kilometres or 151 miles across, with a minimum depth of 848 metres or 2,782 feet. These claims were challenged by another scientist in 1979, who was then disproved almost 30 years later in 2010 when a new paper reclassified the Wilkes Land anomaly from being a possible impact crater to being a probable impact crater, based on the evidence provided by the most recent paper as mentioned earlier. Further investigations have pointed to an impact event including a marked thinning of the crust underlying the topographical depression, with an estimated thinning of between 7 to 10 kilometres or 4.3 to 6.2 miles of crust occurring during the impact. That's pretty crazy to think about. Much of this was melted down into a plasma upon contact, and catapulted out in all directions, with much of it being flung out into space, where it would then fall back down to the Earth, becoming superheated during the re-entry of the atmosphere, contributing to even more chaos and destruction in the process, as this superheated debris would have sparked significant forest and grass fires planet-wide. This asteroid impact is also linked to the unbelievably long-winded and cataclysmic 2 million year long Siberian Traps flood basalt eruption, as the Siberian Traps are antipodal to the point of impact, meaning they're on the opposite side of the Earth from where this bolide struck. Now, this is a contentious issue. Antipodes are still in the hypothetical stage, because it's hard to test what would happen on the opposite side of the planet from where a large rock slammed into it without, there being a large rock slamming into it, and us surviving. But most scientists know this is most likely what's going on, as the energy from these events needs to go somewhere. And the opposite side of the planet from the spot where it struck isn't out of reach from being affected. If these events can thin the crust by 7 to 10 kilometers in seconds, I can only imagine what occurs after the initial impact regarding the transference of energy. It's been speculated that if this was a crater, then the rock that created it was 4 to 5 times wider than the Chicxulub impact event, which took out the dinosaurs. Without a doubt, this type of event would have caused a major planet-wide earthquake, achieving a magnitude beyond anything that Earth's natural tectonic process can reach. So it's definitely possible that this is the impact that set the gears in motion for what is perhaps among the worst volcanic events to occur on our planet, with massive amounts of volatiles being released, affecting the climate of the entire world, and causing negative and potentially fatal impacts to areas near and far from Proto-Siberia. Now, speaking of the point of impact, this is the location of Wilkes Land Basin, where Australia was joined to Antarctica when this hypothesized event occurred. Now, researchers speculate that the purported impact and associated crater may have contributed to this separation by weakening the Earth's crust at this location. And this is actually a relatively common theme. I've read about this often, where an impact event is associated with a rifting event. For example, the Chicxulub impact that wiped out dinosaurs is associated with India's Deccan Traps flood basaltic eruptions, which followed a similar timeline and eruptive journey as the Siberian Traps did some 190 million years before it. So I'm a big proponent of the antipode hypothesis, and I find it to be fascinating. Generally, the actual physical causation for the separation of a continent is the upwelling of a mantle plume, and if the crust is thinned, magma will rise. And when magma rises, the lands on either side of it get pushed away from one another at an ever-increasing rate. These events also tend to propel tectonic plates forth faster than the average speed they are known to drift at each year. The tectonic plate that Australia rests on is one of the fastest moving on our planet, and it could owe that to this event, and the associated mantle plume that preceded it. Another interesting thing to note is that this impact event might also be associated with the massive supervolcanic complex that erupted in New South Wales around this point. And this complex in its own right is associated with the Permian-Triassic extinction because of just how intense it was. This bolide and the associated shockwaves propelled forth by its collision may have actually led to the eruption of many of the supervolcanoes that were present there back then. I've already made a video about this fascinating place, and it's a relatively new discovery too. You can find a link to that in the description. When Australia and Antarctica began to split, a rift valley formed, and this disturbed some of the land around the hypothesized crater. But aside from that, if we were to go down there and get a sample of the rock, we'd be able to ascertain whether or not this is a 100% guaranteed impact crater. These "if only we could get to it" scenarios are common, and it does my head in. This is the only thing that's stopped researchers from getting a sample of the Burkle crater, which lies deep within the Indian Ocean. And as recent events have shown us, the deep ocean isn't exactly hospitable to human life. So until then, we have to rely on geophysical methods to ascertain the likelihood that the Wilkes Land topographical depression has an origin directly related to an impact event, along with other techniques like searching for ejecta and such. So what do you guys think? Do you think this is the cause of the split between Australia and Antarctica? Or was it just an inevitable thing bound to happen either way? Let me know in the comments, and thanks for watching. This incredible stretch of land is pockmarked with small holes that were dug during the massive gold rush that occurred here during the 1850s. In this particular site, miners were chasing a deep lead. What is a deep lead, you ask? Well, it's an ancient river that was buried by lava or sediment. In the past 7 million years, Victoria was transformed into the third largest volcanic plain to exist on our planet. So in this episode, we're going to look at the deep lead in Denali and discuss its creation, Welcome to Oz Geographics. If you went to Denali today, you'd be forgiven for thinking that no volcanoes exist. The eruptions that once covered this land are more or less eroded away, but if you look carefully, you can see the stubs of the ancient volcanoes that once roared to life here. The entire drainage system of ancient Victoria was entirely altered when these eruptions were at their climax. After all, when lava is released, it's just like water. It flows downhill following existing drainage channels. And when these lava flows reach the many creeks and rivers that existed, they'd just flow over them and bury them in time, increasing in thickness with each wave of lava that was released. The affected drainage channels would largely disappear, and when it rained, the water would be forced to carve new rivers out. These new rivers are the present day ones that exist. So back to Denali. This deep lead here was just that, an ancient river that once flowed through here. Many of these deep leads are located quite close to the present day river that exists, but their direction can sometimes be completely skewed, and in some areas rivers flowed the complete opposite way to where they do today. And there's a pretty obvious reason this happens. It's all dependent on the amount of lava that is extruded from the nearby volcanoes. If the ancient river is only covered by a small layer of lava, it wouldn't be enough to completely erase the original topography that existed here, and water will then accumulate after rains and slowly carve out new channels close to the original river as it makes its way downstream. The random nature of the lava flows and the amount of it dictates where the recent river flows lead. In other places, so much lava was erupted that entirely new rivers were created well away from the old ones that existed. The present day material that the miners dug through to reach the deep lead was the eroded remains of this basalt, along with the material that was eroded from the surrounding Ordovician age sedimentary rocks. This deep lead here is largely side by side with the modern day channel that replaced it after it was buried. This modern day channel though is a shadow of its former glory. It's tiny compared to the mighty river that once flowed through here, which was, on average, about 100 meters wide when it flowed. But the land has never really been the same since these eruptions occurred, and you can clearly see that by looking at the geological map, where we have absolutely no alluvial material nearby. It's all colluvial material, meaning water isn't flowing through here enough to sort this material out based on its specific gravity. So the material here is a mixture of a whole heap of different things that are emplaced in somewhat of a rubble-like manner. This means recent gold deposits here aren't properly sorted, and you can find pieces of it anywhere throughout the material, rather than right at the bottom, like what would normally happen when water is allowed to properly flow, and to sort material out in a layer-like manner, such as what would occur with alluvial deposits. And this is a big issue, because that means you have to process all of the material rather than being able to isolate a rich layer of it, creating more labour, which uses more water, and finds a lesser amount of gold in the end. Up north, we see alluvium existing in this ancient 360 million year old granodiorite Devonian intrusion, because of how long this water has been allowed to weather the material down and accumulate. And once upon a time, a little over 7 million years ago, a mighty river would have raged past this area. So in present day, the old lead diggings consists of several thousand remnant mining shafts that were sunk to try to reach this ancient river. Between 30,000 to 50,000 miners worked this lead in 1856, after the discovery of large nuggets were made. The shafts needed to be dug 10 to 20 meters deep depending on the depth of the ancient river to reach the gold that would be neatly sorted, with the largest nuggets occurring right at the bottom of the ancient riverbed due to how heavy gold is. Unlike the surrounding modern-day colluvial material, which was a nightmare to work due to the gold not being properly sorted as previously mentioned. The nuggets that existed in this lead contained many that were over 20 ounces in weight. At the moment, 1 ounce is around 2,700 Australian dollars. Now, this type of mining was super dangerous.
Collapses were common, the ground was unstable, and flooding in shafts was quite a frequent thing to contend with, as these ancient buried paleo rivers would still actually flow to some extent, as the water from rains would seep into the ground and would still pass through them, even though it's buried 10 to 20 metres beneath the earth. So this is the amazing Old Lead diggings in Denali, one of the best preserved sites in Victoria, where you can get a glimpse at what the land would have looked like back in the day during the gold rushes that occurred in this entire state, en masse, for over 50 years. Thanks for watching.
The Devil's Kitchen. That's the name given to this geological reserve in Victoria, Australia. And it's somewhat fitting. After all, this land was, at one point in time, the literal embodiment of the word hellfire, after it was drastically altered within only the past few million years, following some significant volcanic activity. The volcanoes might not be so prominent in present day, but if you know what to look for, you can spot volcanic vents everywhere. But the Devil's Kitchen is remarkable because it has some of the most spectacular columnar basalt in the state, along with many valuable treasures that were sought after and, after much investigation, were eventually found. And this is its story. Seemingly overnight, this quiet land suddenly became dominated by the roar of erupting volcanoes, which spewed forth voluminous amounts of fast-flowing lava emitted from thousands of vents scattered all over the land. When these eruptions first began, there would have been minimal warning, as the ground literally tore open and started to gush out lava. When Australia became volcanically active again, its initial commencement would have been a terrifying sight to see and hear to any animals alive during the time that these eruptions occurred en masse. And yes, these volcanoes would have made their presence known. Their sounds would have been a mixture of the Hawaiian and Icelandic type of low constant roar, accompanied by the explosive sound produced by the Odstrombolian gas slug, which occurred in specific, more explosive varieties. And this area was no exception. It sat for hundreds of millions of years, unchanged by everything aside from the slow withering touch of erosion, only for all of this to change on one fateful day, when lava flows first emerged from the deep and began to bury the ancient land beneath layer after layer of lava flow, which, when solidified, turned into this basalt that you see here. But as you can see, there's a marked difference between the lower portion of the rock face here and the ones on top of it, and that's because this was the deepest part of the lava flow. It was very quickly smothered over by preceding lava flows, and as a result, it took longer to cool. These columns form as a result of said cooling, the shrinking that occurred when this lava went from flowing to solid, and then from hot to cold in the process, cracked these individual pillars of basalt in a columnar fashion. Lava flows are very cool because each is unique, and even parts of a single flow can differ in composition or explosivity. Some are more gaseous, others more volatile, and some are calm oozing flows. And the shape and texture of the basalt that's solidified here is dependent on what type of composition is released and what environmental factors come into play during the flow. If lava contacts water, a steam explosion will produce a solidified version that differs from other parts of the flow that did not reach said body of water. As you can see, some of these basaltic rocks are vesicular, meaning they contain holes. These holes are from the large amounts of dissolved gases released as the lava hardened. Other basaltic lava flows, though, were so low in viscosity that they carried very little to no gas, and as a result, it solidified as this beautiful rock here, known as bluestone, which isn't vesicular, and is a more solid structure as a result. We quarried bluestone to build homes, warehouses, churches, and more in the earliest years of Australian settlement. And damn, you gotta give those hardworking Europeans credit for producing this type of incredible architecture that's just timeless and ageless in its appearance. But quarrying basalt by hand before explosives would have been one heck of a job. In certain places, such as the old homestead in Greenvale near the Tullamarine Airport, you can still see the chisel marks made by the old settlers in areas where this bluestone was quarried. So yeah, there's quite a bit of variance regarding the basalt released in the past 7 million years. But basalt is exceptionally low in silica, unlike the silica-rich felsic rocks that are highly erosion resistant, such as granite. And this is why these lava flows occurred to such a voluminous extent. Because when the composition of magma is devoid of high amounts of silica, the viscosity of it lowers, giving it the ability to flow, and for volatile gases to readily escape the lava too. But because these volcanic rocks were devoid of large amounts of silica, that also means that they are far more prone to erosion. And this is evident by just how easily the waterways have carved through the layers of basalt in a relatively short time. In area where basalt dominates the land, you'll always find these steep gorges formed as the river system slices through the volcanic rock, slowly working its way down to reveal the sedimentary material that had sat on the surface here for about 400 million years. And that very same act of carving has produced the Devil's Kitchen, and what an incredible landscape it is. As you can see, quartz is literally everywhere here. Major deep lead mines operated here in the 1870s and 1880s. Shafts were dug to intercept the ancient river that flowed through here before the basaltic eruptions occurred, so that they could extract the rich amounts of gold from the ancient bedrock. And man, did they put in the work! There are massive piles of river-rounded quartz cobbles and boulders stacked up all over the place, lying alongside significant piles of the worthless sedimentary rocks the miners pulled out of these ancient riverbeds, while they were chasing the much sought-after gold-laden quartz gravels. The work that was put into this area was quite immense. It's forever altered the landscape, that's for sure. When these guys first arrived in this area, there would have been minimal surface quartz present here, except for any that was carried from upstream from a place that wasn't covered over by the basalt, of which there were a few by the time of European colonisation. But in general, if we were to remove all of the shrubs and trees, we'd see many gaping holes from the still open mine shafts littered all throughout this area. On top of this though, what's even more remarkable is the adits dug into the cliff faces here. They horizontally blasted into the basalt to intersect any other buried rivers or tributaries that weren't so evident on the surface. And boy, did they come across some damn good ones. An adit exists from this side of the gorge all the way through the basaltic plateau and out the other end in Happy Valley. And this was apparently an amazing feat to have accomplished at the time. This adit's existence prompted me to delve into an excellent 300-page thesis on the area that explores the region's gold mining and settlement history. The original township that popped up here was actually called Devil's Kitchen, which is pretty metal. It was later named Springdulla and then Tepiggareet, only for the town to slowly crumble and fade away from memory over time. And in the present day, very little remains of this township aside from some scattered ruins amongst land that is now used for grazing. But in its heyday, during the 1870s and 1880s, some crazy stuff occurred here. It was one of the only mines where boats, out of all things, were used to sail across flooded old workings. 3 ships were built and operated for a period of 12 months to sail a distance of 152 metres or 500 feet from the shaft, and this was done at a depth of 100 metres or 330 feet deep. One can't help but wonder whether or not any remains of these boats exist in these shafts today, but the flooding renders it dangerous beyond reason to explore it, unless... Nah, seriously, please don't. So the Devil's Kitchen really is something quite spectacular. There are many places in Victoria where columnar basalt exists en masse. One site that most Victorians know is the one found in the Organ Pipes National Park, which are far smaller than these beasts in the Devil's Kitchen. And that's why this area is a designated geological reserve, because these are some of the best columnar basalt in our state. But one thing that's very interesting about this place is that it's one of the few areas that really emulated Ballarat and Creswick in the amount of water that was present at all times, and was an unyielding element to contend with, as pumps were run 24/7, sometimes to no avail, in an attempt to pump water out of the shaft back up to the surface, where it would run downstream into dams and other areas to be utilised. But it would inevitably seep through the porous bedrock and slowly work its way back down into the deep leads again. And the yields here were equally as rich as the areas mentioned above. Getting anywhere between 100 to 400 ounces of gold a week in these mines was common. Today's price of 2,877 Australian dollars per ounce would have earned you an astonishing 287,763 to $1,151,054. Not a bad week's pay, that's for sure. Mount Warrenheip is one of the many prominent scoria cones that exist in Victoria. Unlike the others though, this is probably the most famous, along with its sister volcano, Mount Bunanyong. It was one of the first really recognisable landmarks to grace and be embedded into the eyes and minds of Europeans, due to the valuable landmark that it served as, which let travellers know they had arrived to the incredibly rich alluvial goldfields of Ballarat, which was rushed in the 1850s by many tens of thousands of people who came from all over the world to try their luck at Australia's recently discovered diggings. People from North America to Western, Southern and Eastern Europe to China and even South America came here in search of fortune. Being the recognisable landmark that it is, Warrenheip was of course cherished by the Aboriginal tribes who thrived in this land for many tens of thousands of years prior to the arrival of Europeans. In this video, we're going to take a look at Mount Warrenheip, from its formation to the large lava flows that it released, to whether or not it could erupt again. And spoiler alert, this area definitely can, and most likely will erupt again soon. How soon though is the question, and what would happen when this hypothetical eruption started? I also wanted to clear up some misconceptions about Mount Warrenheip too. Contrary to popular belief, it is not responsible for burying the incredibly gold-rich Eureka deep lead in Ballarat. This is an old, misled belief. I can actually take you right to the tiny, highly eroded stubs of the many volcanoes that did cover this and the many other ancient rivers that once coursed through Ballarat. And I will do this and release it as a video in the very near future. But Mount Warrenheip did bury some gold-bearing rivers, just not the ones that many books attribute to it. Some of these deep leads we've found, and others we haven't. The major river it buried wasn't really ever properly intercepted, although some attempts and some minor successes were made in the early days. The basalt here is just too fresh and too thick. As a result, the actual deep lead it covered is still down there, somewhere, filled with what would more than likely be many literal tons of water-worn alluvial gold 100 or so metres beneath the basalt. Scoria cones, also known as cinder cones or pyroclastic cones, form after violent eruptions blow lava fragments into the air, where they then quickly cool down, solidify, and fall back down to the ground as pyroclastic fragments. These fragments can range from a few millimeters to meters in size, and sometimes these eruptions blow out massive boulders the size of vans, and in many places around Victoria, you can see evidence of these eruptions and the gigantic basaltic boulders they threw all over the place, sitting piled together in many farm paddocks. When Mount Warrenheip first formed, it began erupting explosively from one central point, exploding forth pyroclastic fragments which would slowly begin to build up the conical shape. Eventually, the flanks grew too high and began to slump in upon itself, forcing a major explosion to occur. The last eruption to occur from this volcano was dated to 1 million years ago, and we can clearly see that it exploded out here, leaving this U shape, where there was once a perfect O shape, just before the climax of the most recent eruption occurred. Before this one though, another big lava flow was released from here, and it flowed south. There are a few parasitic vents around Mount Warrenheip too, but these were largely just small effusive lava flows that appear to have had little to no explosivity related to them. Now, cinder cones only erupt a few times in their life, before the jamming up of the particular area of the fault line that the magma fueling this volcano is using to ascend occurs, causing subsequent eruptions to travel elsewhere and find their own way, so to speak, which basically means finding easier routes to ascend that require very little pressure to break through. That reason is why we have so many of these beautiful conical structures protruding everywhere throughout the middle to western parts of Victoria, accompanied by many dozens of shield volcanoes, small and large. Mount Warrenheip had a few major flows in its life, so it's changed shape and height a little. At the moment, it sits at a proud elevation of 746 metres, or just under 2,500 feet. Because of the rapid cooling that takes place during these explosive eruptions, the basaltic fragments contain many vesicles. Vesicles are these pitted structures found in rocks, and this picture will probably be very familiar to many Victorians far and wide throughout the state. This type of basalt, as you can probably tell, isn't what was quarried to make the many gorgeous bluestone structures that were erected predominantly during the first century of European colonisation here. Bluestone is a type of basalt that contained very little gases in the magmatic makeup, and thus the consistency of the actual rock itself is solid and pretty much uninterrupted. Victoria, unsurprisingly, is the only state that actually quarries basalt, and the reason for that is obvious. We're trying to get to those fucking gold-rich rivers one rock at a time. Just kidding, the reason is because our state is saturated with this volcanic rock. We're the third largest volcanic province in the world, and all of this basalt was erupted recently, geologically speaking, with it starting 7 or so million years ago in Victoria, and slowly moving south in its dispersal. But it's unsurprising to see these rugged volcanic structures here, because basaltic cinder cones are most associated with intraplate volcanism, and that's exactly what's happening here. With no nearby subduction zones or areas of tectonic rifting, the magmatic source for this isn't exactly clear yet. Thoughts were that this was a hotspot known as the Cosgrove Hotspot, which erupted in Australia within the past 35 million years, beginning in Queensland and slowly moving south to Victoria, beginning here around 7 million years ago. This was the most solid theory we had, until recent scans revealed it to be impossible, because the source of this magma is shallow. A volcanic hotspot has a deep magmatic origin, with the basaltic magma journeying straight from the mantle. But again, I needed to reiterate that this is not the volcano that is responsible for burying the Eureka Deeplead. The ones that did are not very remarkable at all to look at in present day, due to the high level of erosion that has occurred. In the past few decades, hundreds of trees on Mount Warrenheip have unexpectedly and suddenly died, and we can't figure out why. Which is a little baffling and somewhat scary, but if it's a magmatic origin, I'm sure we're probably not going to know until the magma actually comes out, because let's be honest, no one takes volcanic eruptions seriously in Victoria, and we probably won't until we're forced to. So this is the story of Mount Warrenheip. If this area was to experience another eruption, it probably won't occur on the actual volcanic body itself. It'd most likely be a new location, where a new hill that could be even more spectacular than Mount Warrenheip could be built. Or not, time will tell. Thanks for watching.
Whilst it may not look like it, this area was once an epic mountain range that was similar to what one would witness today in the Andes. These rocks tell an incredible story, and in this video, I'm going to share that epic tale with you. If you travel to any part of the world and you see this, you can be sure that something major happened. Intense tectonic collisions occurred, buckling the Earth, thrusting it up, and tilting rocks that were originally horizontal, like these, into more vertically orientated ones. Depending on the intensity, rocks can be made almost completely vertical, if not completely. The rock you see here is sandstone. It's located on the boundaries between the Horst and Graben, and has experienced multiple tectonic events throughout the past 530 million years. The grains of sand that make up this sandstone was originally eroded from the ancient supercontinent of Gondwana, and is actually more related to South Australia than it is to Victoria. Why? Because South Australia was the site where Australia pretty much ended back then, and was the point where the ancient Paleo-Pacific Ocean began. The grains of sand that make up this rock were eroded, and they would eventually be carried away by rains that fell eons ago, when primordial rivers would then carry it out to the sea, where it would accumulate, and accumulate, and accumulate some more, until an instability eventually occurred. An event known as a slope failure would then be triggered, and the sediment that had spent so long building up for thousands, if not tens of thousands of years, would, much like a landslide on dry land, be thrust into the abyssal plains, in a phenomenon known as a turbidic current. When these slope failures occur, the sediment is transported for kilometers to very far away distances from their point of origin, and these grains of sand landed here, in what was once an incredibly deep ocean floor. Eventually, this deep ocean floor would experience its first of many tectonic collisions. The oceanic Paleo-Pacific tectonic plate would collide with the continental landmass of ancient Gondwana, pushing beneath ancient Australia and Antarctica, as the two were intimately tied at this time.
It was also around this time that Tasmania would collide with Victoria, and the two would become intimately tied, where they would remain up until present day. When the first of these subduction events occurred, volcanism raged. Masses of basaltic lava flows occurred on the floor of the sea, and this volcanism would go on to become the greenstone rocks that so many gold miners in the 1850s would make note of. But back to our little mate, Mr. Particle of Sand. He was on the bottom of the ocean after a major turbidity current carried him far away from the land he was originally shed from, and eventually he would be buried by more sediment that would experience the very same turbidic event after yet another slope failure occurred, and one after another, these events would occur, laying sediment down horizontally in thick layers. When a subduction event occurred, these layers would experience their very first taste of metamorphism, an event dominated by heat and pressure, created by the literal butting of heads witnessed when two tectonic plates collide. And slowly, over time, these individual grains of sand would become joined, fused by pressure, and thrust up by the collision, going from individual grains to solid rock many kilometers thick. Several tectonic collisions would occur over time, slowly thrusting up the deep sediment, where it would eventually break through the surface of the ocean, becoming the dry land we see today. But it didn't stop there. Major mountain building events would occur here, and where I'm standing right now was once covered by many kilometers worth of mighty mountains that today we can still see the remnants of, though they are a shadow of their former glory. They are little more than worn down stubs, a reminder of the greatness they once held, when major mountain ranges dominated this land. Today, all that's left to remind us of these extremely chaotic events are these tilted and folded rocks. And this is the story of how one tiny little grain of sand would travel from a faraway place to become fused with others and thrust up into what was once a breathtakingly steep mountain range, dominated by major volcanic eruptions, powerful earthquakes, and tsunamis. The earliest forms of life would have trekked the steep inclines that once existed here. But that's all in the past now. With that being said, the rocks still tell an incredible story of transformation to this day. Thanks for watching.
I promise this story about a road cutting is interesting. This cutting is located at Norman Street in Ballarat, Victoria. Aside from looking truly beautiful, the story it tells is one that is just remarkable. The almost completely vertical lines witnessed here allow us to interpret the fact that this landform was created by a cataclysmic series of events. What you are seeing here are beautiful mudstones and sandstones, among other various deep sea sedimentary rocks, that were once laid down on a deep ocean floor. This same ocean floor was where this very ground I'm standing on once lay, over 550 million years ago. The origin of these rocks were actually eroded from the rivers and sent out west to the sea that lay just west of South Australia. But back then, it'd be known as Gondwana, a supercontinent with Antarctica to its south. These rocks then tell us that a series of tectonic collisions occurred, and these collisions had their origins in multiple locations across Victoria and would occur several times, slowly raising the state up from the deep ocean sea, alongside New South Wales and the vast majority of Queensland. When these types of tectonic collisions occur, these rocks are subjected to vast amounts of pressure. They're literally squashed together, broken, faulted, broken again, refaulted, rinse and repeat. And what you have, after multiple series of low-grade metamorphic sequences, is this beautiful outcrop that was created like an art piece after a simple road cutting sliced through this once typical looking hillside. It's almost like an artist painted it. The pink, purple and brown colours so beautifully interlaid amongst each other, with hues interspersed within. But what we haven't spoken about is something that in my opinion, makes this even more beautiful. And that was the mineralization that occurred to these rocks, with the heaviest events peaking at the end of each tectonic collision that occurred in Victoria, over the course of between 550 million years to 360 million years ago, give or take. These events are what made Victoria the incredibly gold-rich state that it was, and still is. And it was because of these beautiful, tasty fellas. And I love these guys. These quartz reefs and stringers were shot into the faults that were created during subduction events. Tectonic collisions and mountain building events, such as what is witnessed here, always come with heavy mineral deposits. These deposits are a result of the metamorphic series of events that occur, where minerals are literally quote-unquote sweat out of the rocks as they subduct deeper into the earth, due to the immense heat and pressure that occurs. Water is also released from hydrous minerals, and this creates a boiling mixture that kind of acts like an underground volcano of mineral-rich fluids. It's like a magma chamber in a way, because what happens is these fluids accumulate deep within the earth, percolating and building up their pressure until it finally reaches a point where they're able to shoot through a fault by physically opening up the structure and being released, where they would then shoot through until the fluids begin to reach a point where they depressurize and cool, and they solidify as this beautiful gold-rich quartz that we have everywhere here in Victoria. So yeah, this road cutting tells a remarkable story in my opinion, and if you're ever in Victoria, you should visit Ballarat, and definitely treat yourself to this site, as it's even more incredible in person. Thanks for watching.
It's incredible to think that this unassuming stub of beautifully coloured rocks right here are literally the roots of an ancient mountain range that has been heavily eroded in the 400 to 440 million years since it was at its peak. I like to try to imagine how tall this ancient mountain range once stood, and how much material was eroded in the time between its creation all the way up to the present day, where the literal bowels of the mountain have been revealed, as we can see here. When I inspect this area, I see so many features, all of which tell their own unique and fascinating story about what occurred here in the distant and not so distant recesses of geological time. For example, on its western edge, I can see signs that an incredibly primordial river once flowed through here. These rounded pebbles are all that we have left today, which hint back to those ancient times, when long forgotten tributaries and rivers snaked through the rugged land here, slowly wearing the mighty mountain range down throughout the eons. In this video, we're going to touch a bit more on this road cutting here in Ballarat. I've already made a video on it, which focused on a different aspect of its existence and on a different part of the story, but in this episode, I'm going to touch on the mighty mountain range that once stood here, along with some of the nuances that exist to explain its formation. We'll take a look at the fault systems, the geological processes that occurred, and we'll discuss the role that an ancient microcontinent played as well, when it collided with Victoria 440 million years ago at a point just east of Ballarat and Bendigo. It would do so after an active subduction event slowly pulled this continental piece of land in until it inevitably collided with Victoria, forcing a continent-to-continent collision to occur, leading to the eventual fusing and total accretion of this microcontinent with Victoria. And Tasmania, which was a part of this tiny microcontinent, would become a part of Australia from that point on. And this collision would help to further form and intensify the mighty mountain range that already stood here when these events occurred. Van Dieland is the name given to an ancient microcontinent that's around 1.6 billion years old. It formed much like the eastern part of Australia would, with it occurring in an ancient seafloor, with sediment shed from rocks from the nearby landmass that's more associated with Arizona and Antarctica than they are with anything that's even remotely Australian, before tectonic events uplifted this microcontinent, where it would exist for about 1.1 billion years before joining up with Australia. During the Ordovician period, 485.4 million years ago, it drifted exceedingly closer towards the ancient shoreline of Victoria, after a wave of subduction events that began in the Ordovician and carried through into and well past the Silurian, began to thrust this part of the land out of the deep sea. The Silurian began 443 million years ago, and lasted through until 419 million years ago, when the Devonian took over. And during this time, the microcontinent of Van Dieland collided with Victoria, which was located east of present-day Ballarat and Bendigo at this time. When two pieces of continental crust collide, they don't subduct. Instead, the two more or less butt heads and smush against each other, crunching and folding the rocks, forming major mountain ranges in the process. This type of tectonic collision is unbelievably violent. It's responsible for the formation of the most spectacular mountain ranges on our planet. And this type of collision is what formed the Himalayan mountains in such a short period of time, geologically speaking. This type of mountain building event is known as an orogeny, and as you'll see in this video, this road cutting speaks of multiple orogenies. But when two pieces of continental crust collide, this type of tectonic collision works to thicken the crust, meaning surface volcanism isn't associated with these types of events as a result of that. But earthquakes certainly are. There is still a magmatic element at play in this event though, as massive bodies of ancient magma chambers still do occur deep within the Earth, as a byproduct of the continent-to-continent collision. But because of the immense thickening that occurs to the crust during these events, these gigantic magma chambers all inevitably cool before ever getting a chance to erupt, as there is just too much overlying sediment and confining pressures keeping the magma contained. And indeed, we can see signs of these massive ancient magma chambers all throughout this part of Victoria, that prove that this very thing occurred as the entire state is filled with major intrusive batholith-sized bodies, showing just how massive the ancient magma chambers that existed during the days of this and many other collisions were, most of which thankfully never erupted. So back to the road cutting. The origins of this mountain range lie in a subduction event that occurred here 480 million years ago. Over time, the seafloor that existed deep within the ancient Paleo-Pacific Ocean slowly rose up with each subsequent tectonic event that occurred here. Then the microcontinent that Tasmania is situated on, which hosts present-day Melbourne, smashed into Victoria and formed a massive mountain range that ran north to south and was probably at least 6 kilometers or 3.7 miles above this present-day point in its original height, and that's a conservative estimate at best. It's no surprise that the Ballarat and Bendigo districts are so saturated with gold, when you consider the variable amounts of tectonic events that occurred here, from subduction to continental collisions to oroclines, the latter of which is something I still haven't touched on yet, but will in a future video very soon. Couple this with all the erosion that occurred here, and you can see why this is one of the richest gold provinces in the world. The faults created by these events are substantial, and the metamorphism that occurred here is what is ultimately responsible for the accumulation of gold that was shot up in a fluidic state alongside quartz, where it would percolate and eventually solidify in the many fractures and faults that existed in the overlying rock. But underneath this massive crustal thickening, we also have the existence of something that's fascinated me for some time, and that's the occurrence of the inevitable volcanic arc that would have existed here during the original subduction events that occurred prior to the continent-to-continent collision. And I think I might have found some hints of its existence in some parts of the state, which is a topic I'm aiming to explore deeper in a future video, as it's never really been touched on, much to my surprise. One of the things that fascinates me about this road cutting are these central rocks here. This is literally the middle of this part of the mountain, and it's known as an anticline, meaning it's a ridge or fold of stratified rock in which the layers slope downwards from the crest. And an anticline basically tells us that if we were to reduce this land down to its bare bones, by removing all of the sediment that exists in the surrounding area, this would be the highest point in this specific bit, followed by a corresponding drop, because anticlines are followed by synclines. And as you might imagine, a syncline is the direct opposite to an anticline. It's a trowel or fold of stratified rock in which the layers slope upwards from the axis. And a syncline in this area is over here, followed by another less impressive anticline, then another syncline, then another more impressive anticline in an area that's a cemetery. But if we were to cut through the road here, we'd see the same type of anticline looking shape in the rocks that we can see in this cutting. And this repetitive syncline and anticline geology repeats endlessly all throughout Victoria and travels far beyond this point. But you wouldn't really know it, because if you continued west from this cutting, much to my extreme disappointment and frustration, the recent volcanic activity released so much damn lava that the valleys, basins, ravines, and really almost all of the western part of ancient primordial Victoria, which is the real Victoria, has been filled up, covered over, obscured, and flattened. And this annoys me. I want the real Victoria back, damn it, not this glass half-filled shit. As you can tell, I'm quite passionate about this. 90% of my life is spent imagining ancient Victoria, and the rest of my time is dispersed amongst this YouTube channel and a few other select things that pique my interest, coupled with, the activities necessary to keep me alive. Damn you, sleep. So back to the topic at hand, if you travel west after this peak here, you'll be greeted by a much flatter looking land, because you are shifting from a landscape that is 450 million years old in its origin, to one that has been covered by young lava flows that were released from pretty much everywhere all over Western and Central Victoria in the past 7 million years, with thousands upon thousands of vents and eruptive centres, small and large, existing literally everywhere, beneath which lies the ancient valleys and peaks that once existed here, much to my extreme frustration. But if you move east, you see the fault line that shows us where the microcontinent that Tasmania sits atop originally slammed into and fused to the crust that now makes up Victoria. And this collision led to an extreme level of faulting, and to these mountains becoming far more pronounced than they otherwise would have become. Because this was a continent-to-continent collision, instead of a reverse fault occurring, we see the existence of a major transform fault, meaning these two pieces of land collided and then began to shear horizontally against one another in a most dramatic way, crumpling, buckling, folding and uplifting the surrounding rocks as a result. So thank you Tasmania, you guys are bloody legends. The sea would have originally been here before this continent-to-continent collision more or less filled in the gaps. When we look at the faults in the actual road cutting, you can see that parts have moved that were once clearly joined. Along with this, you can see the intrusion of gold-bearing quartz, interspersed amongst many of the faults and weaknesses that exist in between the layers of sedimentary material here. They intruded these rocks much later, and they did so by being shot explosively through the faults when they were in a highly pressurized, hot and fluidic state, before finally solidifying here, which was several kilometers beneath the earth when this event actually transpired. The fact that we can see these quartz veins everywhere shows just how much material has been eroded from here since they were deposited. The faulting that occurred here as collisions took place are known as reverse faults, which is when the block above the fault moves up relative to the block below it, and we can see that very clearly here in many parts. Victoria is more or less filled with reverse faults. Aside from some exceptions here or there, it's a land filled with upright, fold-dominated, west-dipping thrust faults. Now, all of these layers of rock were once completely horizontal when they were originally laid down, but as you can see, the layers tilt up dramatically today. It shows just how extreme the tectonic forces were, and during its height, this mountain range travelled all the way up to and past Bendigo. If we look east of here, we have more anticlines visible, including one that's present at the top of this part of the ancient mountain range, before dropping back into a syncline and finally peaking along the limits of the Brownhill Ranges. And as you can probably guess, the Brownhill Ranges are the stubs of this ancient mountain range, and the limits of where they begin is actually the spot where this ancient mountain range was constructed. And we can witness this in person by taking a look at this major reverse fault line here, which is a line where this mountain range was once at its highest. As I mentioned earlier on, the origins of this mountain range lie in the subduction events that originally uplifted this land. But when the collision with Tasmania occurred, the compressive stress really worked to thrust these mountains up, and it dramatically increased their height. This fault is one of many that mark the line of an ancient subduction event in Victoria. Before we wrap this video up, take a look at the many different sedimentary rock types here, and the gorgeous vivid colours they display. It's quite amazing to me just how artistic simple sandstone, slate, mudstones and siltstones can be. But notice the metamorphic foliation that has occurred here. These bands and lines that we can see are foliation that occurred as a result of the regional metamorphic compression that's typical of areas where a mountain belt has formed, just like this one. These rocks develop a structure that reflects the direction that pressure was applied. I love how the center of this part of the mountain is so clearly defined, how the actual rocks themselves reflect the direction of the pressure by forming these, yes, I'm going to say it, chevron-looking shapes in the very heart of this part of the ancient mountain, as compressions squeeze these beautifully coloured sediments from both sides. So this is what a simple road cutting like this can tell us. 550 million years of history that speaks to the existence of ancient rivers that once snaked through this land, to the many subduction events that took place here, topped off by a continent-to-continent collision that occurred when the microcontinent that hosts Tasmania collided with this part of Australia. And this is one of the many reasons why I love geology so damn much. Thanks for watching. Osteographics is a channel that focuses on topics within the realms of science, exploration, and discovery. We release videos regularly, so if you enjoyed this one, please consider subscribing to the channel. If you'd like to support us, please click that like button and consider sharing this video around with your friends and family, as that is single-handedly the best way to help us grow, and is by far the most vital way that you could show your support to us. If that's not enough, though, we also have a PayPal address that you can donate to if that tickles your fancy. Or consider becoming a member and supporting our YouTube channel by clicking the join button. Each donation and membership is deeply appreciated beyond words, and helps us to continue producing this kind of content. Thank you again for watching. I'll see you all real soon with another video. Cheers, guys. In an ancient epoch of Earth's vast history, the lands of Tasmania and Victoria stood as separate tectonic entities. 500 million years ago, Victoria was a deep sea, slowly thrusting up due to tectonic collisions. Tasmania, which had existed as a microcontinent for over 1.6 billion years, would soon join the fold. And it was during this collision that the spectacular Yuyangs were born. Today they tower over the flat land, and they're visible from distances quite far away. To the untrained eye, they might look like a stratovolcano, but the Yuyangs are anything but that. In this video, we're going to discuss the Yuyangs, how it was born, what processes were involved, and we'll discuss whether or not this was the site of a major volcanic eruption. As eons quietly passed, the stage was set for a dramatic convergence. Unseen forces orchestrated the grand collision between Tasmania and the southeastern part of Victoria. With immense power, the two landmasses collided 430 million years ago, shaking the very foundations of the Earth. The clash of these titanic entities sent shockwaves through the crust, causing rocks to buckle and fold under immense pressure. Vast mountain ranges rose from the depth, their majestic peaks reaching towards the heavens. The Brisbane Ranges, the mountains in and west of Wombat State Park, and any others that stretched north were all constructed during this event. And pre-existing mountains were further deformed and heightened in the process. Among them, the Grampians stood taller by its conclusion, with this event working to further elevate the already dramatic mountain, along with the heightening of other ancient mountain ranges in the west, from the Pyrenees to those constructed by the same tectonic collision that produced the Ballarat volcanic arc, a testament to the incredible forces unleashed during the collision. The immense upwelling of magma was alongside the construction of mountains. This magma couldn't ever reach the surface to erupt due to the tremendous crustal thickening occurring as a byproduct of the continent-to-continent collision. The reason for this is the inability of a tectonic plate to subduct when two continental plates meet. In this context, subduction can only occur if an oceanic plate meets with a continental plate. So rather than the mountains being a byproduct of subduction events, they are instead the byproduct of two grinding plates, which builds far more tremendous mountains and thickens the underlying crust than any subduction events do. So because this magma couldn't reach the surface, it eventually cooled to the point of solidification. Vast amounts of magma are still produced during these collisions, much like they would be in subduction events. But because this magma cannot reach the surface, owing to the thickening of the crust, it eventually cools to the point of solidification. And this is what happened to the Yuyangs. It was once a massive, churning magma chamber. It stretches way beyond where it currently outcrops. It's a colossal batholith. It would have been near or at a supervolcanic eruption if this magma chamber erupted, but it never did. It, along with many other magmatic entities that were just as large, if not larger, that were also a byproduct of the continent-to-continent collision that occurred, that began 430 million years ago, and fizzled out around 360 million years ago, all solidified beneath the Earth. As the eons passed, the forces of erosion swept across the land, sculpting the landscape with their gentle touch. Wind, water, and ice worked tirelessly, removing the softer sedimentary rocks that once covered the erosion-resistant silica-rich granitic rocks at the Yuyangs, and over time, erosion worked much of the overlying sediments down, and several rifting events occurred, which thinned the crust here. One of the rift events that occurred near here is the one that produced the Port Phillip sunklands, which is responsible for the creation of Port Phillip Bay. However, this is just one of many that have occurred in Victoria, with the Antarctica-Australia separation being another. On the magnetics, I can trace the Yuyangs to the plate boundary where the collision between Victoria and Tasmania occurred. If you're a local, I recommend driving towards Ballarat and stopping right where this line is, and you'll see the marked transition where the mountains begin and the flat western volcanic plains end. It's around Bacchus Marsh. Today, the Yuyangs stand as a testament to the Earth's dynamic nature and the enduring power of geological forces. And as each new discovery and scientific revelation emerges, the story of the Yuyangs continues to unfold, reminding us of the ever-changing beauty and deep history embedded within the Earth's ancient embrace. So when you look at the Yuyangs, remember you're looking at an ancient magma chamber that's older than the dinosaurs and was once buried many kilometers deep within the Earth, beneath a massive ancient mountain range. What a truly incredible story. Thanks for watching. See this steep rise in elevation? This annoys me. It's annoyed me for years. Why is there such a marked and sudden uplift in this area? What caused this to occur? And why is the direction of it opposite to the typical east to west facing fault systems in Victoria? These were some of the many questions I asked when I first came across this strange geological oddity. But I think I've finally figured it out. And if I'm correct, the implications of it are massive in more ways than one. This is going to be part one of a series that I'll be making as I attempt to solve, or at the very least, gain a greater insight into the burning questions I've had for years surrounding the geology of the Ballarat and Creswick region. This story begins with my attempts to decipher a weird geological oddity at Black Hill, which I will delve into in greater detail in a coming video. But essentially, everything began with this point here. This fault, this horizontal line that breaks apart in this section, is something that stood out as unbelievably strange to me when I saw it many years ago. In Victoria, one would expect to see the typical east to west facing faults, as a result of the state being formed by multiple subduction events over time that dipped underneath the west from the east, thrusting the land up out of the deep ocean in the process. This is what some of them look like. But now we have this horizontal fault. Years ago, I remember looking at this and shouting, "Why? Why do you exist?" And this lack of understanding would plague me for years. I would wake up at night, soaked in sweat, where I would then proceed to get up, walk to my window, put one hand on the glass and whisper, "Black Hill," until my missus told me to shut up and get back to bed, to which I begrudgingly obliged. In all seriousness though, this fault here is the start of our story, and this story will span beyond this episode. I'm setting the scene for the next few videos, and in one of them, I'm going to reveal the location of a gold-rich line of reef that was sought after for years, but was never found. Yes, you heard that right, I'm going to show you exactly where it is. The knowledge associated with it will be a revelation to literally every prospector or geology enthusiast in Victoria. But to get into it, something pushed this part of the land up by between 40 to 50 meters. This is weird. On top of that, we have a break in the fault, meaning something exerted so much force in this area that it literally snapped this fault in two. And this is the first clue. The second is, well, obvious. Why is this scarp slope so pronounced? If Australia was an earthquake-prone area, I wouldn't be so baffled. But since we get minute ones at best, with us only very rarely experiencing major events, although they still do occur, but they aren't common enough to explain what we are seeing here. So this escarpment isn't formed by a traditional earthquake, and it's not formed by the erosion of soft rocks versus more erosion-resistant ones either, because this is all ancient sedimentary bedrock from the Ordovician era, which was deposited during a time when Victoria was a deep ocean. So the rocks are little more than mudstone, siltstone, slate, sandstone, etc. There's no granitic outcrop or erosion-resistant outcrop that's stopping the slope from being eroded. So what is it? Well, I think it's one of the many Horsten-Graben sequences in Victoria. It's the only thing, in my eyes, that perfectly fits and explains this to a T, including the breakaway that's witnessed with this fault, which would occur if something was pushing against it in a northwestern direction. But if any geologists are studying this, I'd be interested to hear what you have to say. The rift event between Australia and Antarctica created the Horsten-Graben phenomenon, which I've covered in past videos. One part of the land drops, and the other either elevates or remains static whilst the adjacent block drops. The outcome? Alternating sequences of highs and lows, varying in their level of spread. Some Horsten-Grabens are short, others quite long, going for kilometres or more in certain cases. So when Australia and Antarctica separated, Victoria was faulted in a very unique way. For the first time in its history, it was faulted in a north direction. This knowledge is actually pretty new to us, so the implications of it are still being explored. But it explains why this fault snapped here. So let's take a look at the implications here. If the land I'm standing on when I took this video is a graben, then the mountain range that Black Hill is a part of, which, by the way, is called the Brown Hill Range, would be a horst in this area. Brown Hill was originally a typical east to west facing mountain range, and it still is. But in this area, a north to northwest facing fault was added to it, and I believe that this is why this broke apart in a direction that lines up perfectly with what would happen if massive pressure was applied to it in a northwestern facing direction. In the preceding episodes, we're going to take a look at some pretty fascinating things. Firstly, I believe Black Hill was the site of the original river that predates even the deep leads that run from it. I know that might sound strange, but bear with me and try to keep an open mind, because I promise my reasoning for thinking this is pretty damn sound. On top of this, like I mentioned before, I'm going to show you where a gold-rich line of reef is located, and I'm going to explain why the old-timers missed it. And all of these topics tie into this video, and I believe will explain the deep nature of the leads in Ballarat, with the depth of shafts being ludicrous to say the least, especially when compared to the couple of feet that was required to reach bedrock in places just a little north from it, compared to the dozens or hundreds of feet required here. So this is episode 1 of what I consider to be a fascinating geological series with far-reaching implications. I hope you guys will join me on this journey of exploration and hypothesizing. Make sure to hit that subscribe button and click the bell icon to be notified of when it's uploaded. And as always, thanks for watching. This story is one that intimately ties the complex geology of Victoria with a section in a line of reef that was known to exist and was much sought after, but was ultimately never found. Much effort was placed in attempting to locate it, but the miners and geologists of the time didn't have one crucial piece of information that's required to decipher what is going on here. In this video, I'm going to attempt to solve the mystery of the missing southern section of the Temperance Reef, which was an insanely gold-rich vertical line of quartz that stretched over a long distance, and that, in present day, still exists beneath the feet of many who call Ballarat home. And I'm almost certain that I know exactly where it is. A few weeks ago, when we discovered a gold-bearing reef and started the GoFundMe, I mentioned in the video that I intended to give back to the community, and to begin to release some game-changing info. The link to that video is in the description. Even though we never reached our end goal, I can't tell you how appreciative I am that people so generously donated to help us out. I'm a man of my word, so this episode will be one of many to follow that will consist of me walking my talk and sharing some of the most valuable and widely unknown information from the many years that I've spent being an obsessive geological nerd. This episode is technically part 2 to the video that I released yesterday regarding the strange escarpment that exists in this region, and it's worth watching that first before proceeding, as this is centered around this mountain range here, known as the Brownhill Ranges. So bear with me and make sure you're subbed so that you are informed when I release these videos. Please do me a solid and hit that like button too. That's all I ask in return for the valuable information I'm going to share with you over the coming weeks and months, beginning with this video. The Temperance Reef was, and still is, a highly mineralized gold-rich line of quartz. It was deposited into the bedrock of Ballarat some 430 million years ago, give or take, during one of the numerous subduction events that occurred here. The part of the reef that was discovered is here, and multiple companies worked it. But by far, the most renowned company was the Temperance Mine, which was the standout quartz mine in the area northeast of Ballarat, known as Narina today, or Little Bendigo in its heyday. The mine produced 1,530 kilograms of gold out of a total of 3,511 kilograms for the whole of that field, meaning they produced almost half of all the gold that came out of Little Bendigo / Narina. But the richest mine that worked this reef was the Band of Hope, situated just a little north of Temperance, with them yielding an incredible 2 ounces of gold per ton of crushed quartz, which is insanely rich. Temperance have a street named after them just a stone throws away from where this major mine once operated, and the shaft they used still exists to this day. This shaft was visibly open only a year or so ago, but blackberry vines have grown over it. Even with that, you wouldn't want to hop into this hole for reasons I'm about to mention. For well over 20 years, this company worked this reef down to the deepest depth out of any mine in Ballarat, with them approaching 1,000 feet in depth, or almost 305 meters, and the gold was damn good. But this story is less about the company, and more about the mystery regarding why this reef suddenly disappeared from this point onwards. In the book The Astonishing History of Ballarat, Volume 3, the following line appears. The Temperance Reef was worked from about 1853 to 1893, when it was found that its continuity going south was broken by a cross course, beyond which, I believe, it was never traced. This cross course is what I will address in this video, but as you will see, multiple attempts were made to locate it. The first company that tried and failed was the Express Quartz Co., located here. The owner of this mine got into a conflict with the boys from Temperance, and was tarred and feathered in one instance after being beat up when attempting to literally encroach on their claim in the most disrespectful and forceful manner imaginable. He kinda deserved it. Eventually, the Express Quartz Company began operations, but soon failed, and the claim and the mine was bought up by the Temperance Company to be reborn as the South Temperance Mine, after which the trail goes cold after 1875. It too had failed in locating the southern section of the Temperance Reef. Other attempts were made by these men to locate it, with 2 other shafts being sunk to the southwest of the South Temperance Mine, and they were also called South Temperance Mine, but again, nothing came of it. The last mine that attempted to intercept it was the Russell Square Co., which worked ground post-1880s that was associated with the famous Eureka Deep Lead, roughly 30 years after it was discovered. Their intention was to reach this deep lead and 2 suspected tributaries, to get any of the alluvial gold that earlier miners missed, and along with this, they sought to find the missing Temperance Reef, and were expected to as well, with many people confident that this was exactly where it ran, and that the company would find it any day now. Well, they didn't, and you're going to find out why in a moment. This bit of knowledge that I'm going to share with you is a game changer, especially if you're a prospector or miner. But if you're like me, and you just love geology and the ability to interpret the land as much as I do, then this information is also essential to do that with any level of accuracy in Victoria. So whilst this concept is being applied to a very deep mine in this video, it's also applicable to shallow ground, and the implications of it are truly far-reaching. This information, when appropriately applied, opens up a whole new world of prospectivity in this amazing state. The only thing that's stopping me from proving my hypothesis is the ability to legally sink a shaft to the required depth. Believe me, if I could do what the old fellas did and head to the store, buy some dynamite, peg out a claim and begin blasting, I'd be doing that right now to prove it. But the value in this isn't so much in the reef, at least it isn't for me. It's more in what the implications are regarding how it broke off from the main line, and how it got moved away from it. This information will probably interest the Ballarat gold mine, so if you guys decide to get a claim, just remember who gave you the info, and at least give me an infinite amount of free tours down there so I can nerd out on the geology. That's all I ask in return. Anyway, this explanation and the ultimate realization that it provided to me regarding the location of the reef originally began with me attempting to decipher a weird geological oddity at Black Hill. Black Hill was a massive open-cut gold mine. Low yielding, but odd in that because it was so extensively worked, it was mapped to perfection. But in the mapping, instead of seeing the typical east to west facing faults, which are to be expected in Victoria, as this entire state was more or less formed from subduction events that dipped underneath the west from the east, thrusting it up in the process. And yesterday's video touched on that, and it's definitely worth watching this video first, so that you can understand what I'm about to say in more detail. Basically, it appears to me that a Horst and Graben event altered this land in recent geological time. When the shafts were sunk to locate the missing Temperance Reef, this valuable bit of information was never taken into consideration, and as a result, the miners never sunk to the appropriate depth when they made their shafts. They sunk it to around the 60 to 90 metre mark, not realising that this part of the earth, known as a Graben, had sunk in recent geological history, whilst the area where they found the original reef was on top of a Horst, an area of elevated land that had become uplifted. So whilst these sections of the reef were once joined, they had now broken apart, and the southern section of it became depressed along with the land, because it lost its buddy to the north, and there was no geological psychiatrist available back then. I mean, because the land it was located on sunk an additional God knows how many meters, and there's a chance it sheared off a little to the east or west. One thing to take into account is the rule of erosion that applies to uplifted sections of land. The higher it goes, the more pronounced erosion is, and the byproduct of this erosion was deposited on the depressed section of land, and eventually it was further buried by recent volcanic eruptions. But it's not only the fact that this southern section of the reef might be, at a guess, 200 meters deep, it's also the fact that erosion was more pronounced on the Horst section, meaning the Temperance Reef that was found and worked was sitting on a section of land that had eroded to a much more pronounced extent than the depressed block, so it's not even clear if this reef was outcropping when this land began to shift. The Express Quartz Co. stopped their sinking at a depth of 76 meters. They'd given up by this point. But really, they needed to sink an additional 100 meters, maybe a bit more, assuming they were sinking on the right location to begin with. And the fellas from the Temperance mine made this same mistake in their other two shafts. They just didn't sink deep enough. So because of this, the implications are widespread, and they go far beyond just this point. Western Victoria is filled with numerous Horst and Grabens. Many rivers were dried up by these events, and many others were sunk deep into the earth. The shallowest parts of the deep leads are located here, and the deepest in the Grabens. So right now, in present day, I'd be willing to bet an arm and a leg that the southern section of the Temperance Reef is deep underneath Ballarat East. And if you listen carefully, you can hear it mocking us for our futile attempts to locate it. Maybe one day we'll sink a shaft deep enough to reach it, and we can pay it back for its deception by blasting the hell out of it with explosives and crushing it into mere dust, so that we can extract the value that lies therein. Or maybe it'll be spared the same grisly fate that the northern section of it experienced, beginning over 160 years ago. Thanks for watching. This is the final episode to wrap up the Black Hill series, and we're going to focus on the fascinating fact that this uplifted area was actually once the place where an ancient river flowed. This river preceded both the present-day Yarrowee River and the deep leads that would flow from Black Hill post-uplift in Ballarat, only to be covered by recent basaltic eruptions, leading to the birth of the Yarrowee River that flows through here today. If you go to the Yarrowee over here, it's not hard to realise that this river is actually pretty new, geologically speaking. It's small, and whilst it does widen out as it continues its journey south, and then southeast towards Geelong, it's only between 4 to 7 million years old, which compared to the deep leads that preceded it, is very young. Because before this river, we had several older and much larger rivers that flowed south from this area. These rivers began their life during the Horst and Graben events that Ballarat would inevitably experience as a result of the split that occurred between Antarctica and Australia, which led to this part of the land becoming uplifted whilst the adjacent blocks sunk, forming new horizontal faults in a landscape that previously never contained anything remotely resembling these. This fascinates me immensely. I believe the reason why the Ballarat, and more notably the Creswick region, had the most pronounced recent volcanic activity occurring are because these areas are located at the very top of the Great Dividing Range in this region, essentially acting like a pinch point, forming much larger and more pronounced faults than what can be seen in the surrounding areas. Whilst the majority of the western and middle parts of the state are volcanic, this region has some of the most eye-catching volcanic features, especially in the Creswick region. This means that prior to the split of Antarctica, this area here was level. There was no uplifted and depressed region like there exists today, and it's possible that this uplift is actually still occurring to a very minute extent. So before the immensely gold-rich deep leads that would flow from Black Hill was the site of an ancient river. At least it was in the southwestern part of it, right here, where this split in the fault occurred. How do I know this? Well, physical evidence to my surprise does still exist, even with the Black Hill Mining Company's pronounced activity of literally pulverizing so much of the quartz that once existed here into dust to extract the gold contained therein, that literal ravines and chasms were created inside a once somewhat typical looking hill. But we have this incredible account, which was probably nothing more than a fleeting observation to the person who wrote it. And he wouldn't have had any idea that over 170 years later, some dude would be making a YouTube video about it and noting just how important this lad's observation actually was. This is what he wrote on October the 31st in 1851, which was the year the gold rush began in Victoria. The Black Hill is a particularly interesting geological feature. A spiral ridge of rocks appears on the southwest face, exposing a vein of quartz of great thickness penetrating clay slate. Nearer the summit is found steatite, greenstone, and mica slate. These again are found at a point in the form of clays and breccias. The quartz, though existing in masses of perhaps a ton in weight, is invariably rounded and waterworn, and in its position generally affording undeniable evidence of an aqueous deposit. This observation didn't make sense to me in my formative years when geology was just beginning to take a grasp on my every waking moment, but I revisited it recently whilst attempting to understand and ascertain how pronounced the Horst and Graben events in Victoria actually were, and a light bulb moment went off in my mind, which obviously blew my mind and has led to this series. The aqueous deposit was what remained after eons of river action occurred here, and I can tell you right now that I'd do anything to go back to this day in 1851 and see it with my own eyes. This tells me that this section here in Black Hill was the river, and that means that post-uplift the river gravels and associated deposits began to flow downhill to become deposited within the deep leads that would invariably take the place of the ancient river that was now slowly, inch by inch, turning from a river into a hill, and drying up with each passing year. In my eyes, this explains why the gravel pits deep lead existed. The gravel pits has always been a weird geological oddity to me. Why is this deep lead literally filled with so many feet worth of gravel? Why aren't other ones the same? What makes it different to the other leads? Where did all this gravel come from and why is it here? Well, I think that this is the best possible explanation for it. It's still not obvious to me whether or not it flowed north to the Murray or south to southeast towards the sea, but if I was to guess, I'd say it was vertical through this break in the fault, and that would make sense considering the mining activity that has occurred here. But I truly do believe this explains the gravel pits, as once Black Hill began to be uplifted, everything began to flow down into the newly forming deep leads that took the place of this ancient river, and as you can see, quite a few did. On geological maps, no areas list any deep leads beginning here, yet when we go here we can see alluvial work was definitely done, and the miners, perhaps unknowingly, mined what they thought was nothing more than a simple drainage channel, when actually it was the remains of an uplifted ancient river that flowed at a time when this hill was literally level with the ground adjacent to it, and evidence of this fact can still be seen today in the river rocks still located all around this alluvial channel, which prove it was alluvial and not colluvial, which would have displayed much more sharper, more angular rocks. These are 3 perfectly worn down and smooth rocks that I got from the area and brought back home, which prove that an ancient river once flowed through here. As you can see, they are very rounded in their shape, proving this area was the site of an ancient waterway that was an important feature to the primordial landscape and wasn't just a minor creek or small gully. So I'd bet this area had some damn good gold, and the lads that worked around here probably cleaned up well. But the description of a spiral ridge of rocks was something that always stood out to me when I read these accounts. Why was there a spiral ridge? How did it form? But now it's clear to me that this spiral was a result of the erosion-resistant quartz reefs remaining, whilst the surrounding less erosion-resistant sedimentary and volcanic rocks got broken and worn down around it, and carried away over time, leaving what was once an incredible feature that was mined, and the remains of it no longer exist, unfortunately. This Horsten-Graben action more than likely depressed the many deep leads that would inevitably be mined at a depth of several hundred feet during the gold rush. Unsurprisingly, this form of mining was ridiculously dangerous, and it's also more than likely why Ballarat has a significant amount of erosion, with it being insanely gold rich, but containing gold reefs that are actually pretty low yielding per ton, which is perhaps unsurprising to anyone who watched the previous video that I made on this, which explained this phenomenon. Link to that in the description. And all of this has occurred because this landscape has been continually uplifted and is located at the very top of the Great Dividing Range in this part of the land. And the higher a mountain rises, the more pronounced the rate of erosion will be. So today, this mighty hill has almost no indications aside from these water-worn rocks that a flowing river tore through here. But when the early observations of this place were noted, it invariably shows the fact that this was indeed the place where an ancient river flowed eons ago, during a time when Victoria was a very different place, well before the deep leads, which in themselves are ancient enough. But who knows how long it existed here, and what existed before it. But those days are all gone now, and all we have is this incredible mountain range today, and the old accounts of those that once trekked through here and initially observed it in its original pre-mining state, all of whom have since passed. Thanks for watching. I love geology for the simple fact that it tells the best stories, and this story is no different. This immense bowl-shaped feature is located in the centre of a volcano in Australia known as Mount Bunanyong. Upon first glance, one might understandably guess that this crater-like structure was the centre of the eruption that last occurred here. But another thing about geology that is so damn compelling to me is that things aren't always as they seem. Mount Bunanyong first roared to life at some point between 100 to 150,000 years ago. Its first eruption built up a tall scoria cone, which has since been heavily eroded and reworked by the 2 subsequent eruptions that would follow. This first explosive eruption, and I use the term explosive very loosely here, even though these eruptions were somewhat hazardous to any life in the immediate vicinity of them, they weren't really the monstrous types of explosions that one would associate volcanoes with. These were more like a Hawaiian type of eruption. They released lava flows and did have some minor explosive elements to it, but it was largely confined in its level of destruction. The most hazardous aspect of these types of volcanic events would have been the volcanic bombs that were blown out in all directions. But again, the power that's driving these explosions is quite limited, so the large bombs wouldn't fly very far. And some of them were quite large, with them exceeding a metre in size. But in general, the size of the tephra reduced as it got further away from the volcanic centre. The interesting thing about Bunanyong though, is the fact that it had this explosive element. And it's the same with what I like to call its sister volcano, Mount Warrenheip, which is located on the same fault line as Bunanyong, and is positioned only a short distance away from it. Warrenheip also had an explosive element to it, and a single eruption also produced a scoria cone, several hundred metres high, just like Bunanyong has several times throughout history. It's very clear to me that the two share a common theme. The magma that fueled both of these volcanoes had some kind of chemistry change as it rose up and penetrated the crust, and this would make sense, considering they're both seated atop an ancient 360 million year old massive magma chamber that existed in its molten state during a time when Victoria was a very different place, when major volcanic activity and earthquakes were common, and these weren't tiny volcanoes. Oh no, they were the big ones, the planet-altering kind of big. And this part of Victoria's major eruptive history has a very strong link with the timing of the Devonian extinction. But I digress. The fault line that both of these volcanoes sit atop is the one that was formed from an ancient subduction event. And as a result of this tectonic activity, a huge magma chamber existed beneath this very area back then 360 million years ago. But it never erupted. Instead, it cooled and solidified to form the massive granodiorite intrusive body that exists here today. And it appears that the recent volcanic eruptions that occurred here melted some of the ancient granodiorite as it rose up through the bedrock and made its way towards the surface, which would ultimately contribute to a chemistry change that would render the magma more explosive, due to a slight enrichment in the level of silica within the overall composition. If we move west away from these two scoria cones, we find typical shield volcanoes, which are formed by volcanic eruptions that contain very little to no explosivity, and thus the actual structures themselves are more gently spread out. There's no major intrusive body beneath here, and the magma that rose up more or less remained the same chemical composition, with only a slight variance in said chemistry from whatever sedimentary rocks the magma came across as it rose. So when the very first eruption occurred here, Mount Bunanyong was both explosive and effusive in nature, with scoria being released along with lava flows. This is scoria, a dark coloured volcanic rock that's highly vesicular, meaning it has many of these cavities that were formed when the gases that were once dissolved in the magma came out of solution. And because the chemistry of the magma was more viscous, it formed a scoria cone instead of a shield volcano. So in its first iteration, post-eruption, Mount Bunanyong existed as a steep scoria cone that was formed from a singular event, and this event also produced a major lava flow, known as the Clarendon Flow. This release would smother out and bury a 6-kilometre stretch of land in a south to southeast direction beneath lava, forever altering the ancient landscape that had sat here geologically frozen, so to speak, with very little occurring here for well over 300 million years. Between 50 to 100,000 years ago, a second major eruption would occur here, forming this beautiful deep bowl that we saw at the beginning of this video, which isn't an eruptive centre. It's actually the remains of a now dried up lava lake. When this lava lake existed here during this second eruption, it steadily filled and eventually burst its banks, with a huge molten river streaming from this point and exiting the lava lake in a western facing direction, which would flow toward and make up the present day land that part of the town of Bunanyong sits atop. And to get up to Mount Bunanyong, you have to drive up this lava flow, which gives you a really good idea of just how extreme it was, because it's pretty bloody steep. These events, along with hundreds and possibly even thousands of other eruptions, small and large, that occurred here, would produce a double whammy. On one hand, it would produce some of the most fertile soil in the state. On the other, it covered damn near every ancient river, and attempting to get to these ancient rivers would be a task that would go on to kill many miners that were brave or foolish enough to try, in order to reach the gold that was so abundantly strewn throughout the tens to hundreds of kilometers worth of ancient rivers and tributaries that once existed in abundance, but were now completely buried beneath freshly erupted basalt. A third eruption would occur here at some point in the past 12,000 years, which absolutely decimated the previous scoria cone that existed and created a new one. And that's why this volcano looks kind of weird. It once looked very much like Mount Warrenheip does in present day, with it having a beautiful, somewhat pleasing circular mound type shape to it. But it's been so torn apart from all the volcanic activity that it looks quite strange to gaze upon today. But it's fascinating nonetheless. One more very cool thing that occurred here was an eruption style known as fish events, when the earth literally opens up and lava gushes out like water would out of a broken fire hydrant. We see these eruptions occur in Hawaii and in Iceland quite frequently, and they can create a phenomenon known as a curtain of fire. I hope to one day see a curtain of fire in Victoria. I'm half kidding and half not. This state is still active, guys. But as much as I'd love to witness Mount Bunanyong's past lava flows, I can sit with some satisfaction in the knowledge that this area will probably be blasted and covered by lava at least one more time, before it becomes volcanically dormant yet again, like it had been for hundreds of millions of years before the most recent hotspot activity began, and like it will be again when we finally move away from its fiery reach. Thanks for watching.
Long ago,
Victoria was part of the colossal supercontinent of Gondwana. Over vast geological timescales, the relentless march of plate tectonics tore this supercontinent apart, causing significant transformations in Victoria's landscape. One such transformation was the creation of the Otway and Gippsland basins, during the separation of Australia and Antarctica. The region that would one day be known as Melbourne was a land of mountains and valleys at this time. But as the late Oligocene transitioned into the early Miocene, significant geological transformations occurred here, forming the Port Phillip Sunkland. With the conclusion of the last ice age, sea levels rose, flooding the lower areas of the Sunkland and creating the Port Phillip Bay we know today. I've received many comments throughout the years claiming Port Phillip Bay is an ancient supervolcano. I'm going to address that question/statement, and I'll also be showing you the volcanics that underlie the bay in this video. We have some very cool things to look at, and we'll be using geophysical techniques to peel back the layers to see what anomalies lie beneath the salty waves of the bay. Before it became a bay, the Sunkland region was characterised by impressive mountains and valleys shaped by powerful geological forces, including compression and orogeny. Rivers winding through this landscape likely carried alluvial gold from the surrounding goldfields, hinting at the hidden treasures within the earth. The Melbourne zone witnessed numerous tectonic events, including the collision between Tasmania and Victoria around 430 million years ago. Yet the Port Phillip Sunkland Formation stood out as a special event in this narrative, and was potentially further driven by magmatic activity. Regarding remarks about this bay being a supervolcano, that isn't true, unfortunately, as it'd make great clickbait, true? But no, this area is a rift zone, so before the most recent rise of sea levels, it was a depression that hosted vast swamplands. Underneath the waters of Port Phillip Bay, traces of the newer volcanics province are visible, with evidence of volcanic eruptions. One of these eruptions occurred before the area was submerged, while another seemingly happened after the bay had filled with water, indicating a dynamic and active geological history. Intriguingly, there are indications of a hidden ancient river beneath the bay. This river, which was covered by lava from one of the volcanic eruptions, has turned into what is known as a deep lead, a buried paleo river. The Paleo River, the ancient outlet of the Yarra, contains iron-rich basalt, making it detectable through magnetic scans. Being a deep lead, this undoubtedly harbours a rich history, and quite likely carries a significant amount of alluvial gold. But prior to this, well, that's a different story. This land was as mountainous as the areas to its west and east. But now it's obscured beneath the flat, seemingly low-lying ground that Melbourne was built upon. Even though this subsidence occurred though, the rocks don't lie. All one needs to do is drive along the Eastern Freeway to see the many folds exposed by the cutting for vast distances, showing anticlines, refolded faults, and more. The effect of this rift zone on the land surrounding it will be a topic for another video, as it likely led to recent deformation. And I will most likely make a video on the road cutting shortly too, because if you thought I was obsessed with the one in Ballarat, you have no idea how much I'm obsessed with these ones now. If I could camp out and observe it day and night, trust me, I would. I just want everyone in Melbourne to stop using the Eastern Freeway for, like, I don't know, a week, so I can walk up and down it, mapping the faults, digging holes, and marvelling at the wonders of this subsided land, which has hidden its true mountainous nature for so damn long. When I recently moved back to Melbourne, one of the predominant questions I needed to answer was what happened to the mountains here. Surely it couldn't have out-eroded the mountains to its east and west. And now I know it didn't out-erode them, it just experienced massive subsidence and crustal thinning as a result of this rift. And I don't know why this rift has occurred. I can't really wrap my head around it, to be honest. And neither can the geologists that are currently studying it. It's weird. I don't know what it's associated with, and it's really bugging me. It's like an itch you can't scratch, you know? Not in a junky way, like, you know, it's like the middle of the night and I have an itch right in the middle of my back, right in that spot that you can't fucking reach. So yeah, anyway, back to it. So along with that, think of the rift event like the uncoiling of a slinky. It would have opened this land up, thinning the once very thick crust out, and it did so within the past 30 million years. Like, what an absolute mindfuck. So Melbourne is undoubtedly full of minerals everywhere. I'm beginning to understand the geology of this area so much more now, which is instrumental in aiding any mineral exploration that I undertake here. Now, to be clear, I'm still trying to ascertain the extent of the rift. It needs to be clarified that research is still ongoing. I'm attempting to utilise magnetic and gravity scans to see whether or not I can assemble any loose pattern by cross-referencing them with the topography of specific areas. Doing so will allow me to greater hone in on where to explore. Though early, I believe I have a rough idea of the extent of the actual rift itself, and this is 100% speculative, but in my eyes the area of Port Phillip and Greater Melbourne has opened up from here, and fault lines could be the extent of it. So yeah, this rift is very understudied and suspected to be inactive, but its status could change with more research. If it is active, then recent earthquakes in Melbourne would force geologists to have an additional element to consider for the causation of it. So yeah, like I said before, adding to the mystery is a series of volcanic activities known as the Older Volcanics, which occurred some 20 million years ago. Is there a link between these and the formation of the Sunkland? This question remains a cryptic chapter in Victoria's Geological Chronicle. Despite ongoing research, many details about exact boundaries and full extent of the Port Phillip Sunkland still need to be clarified. This merely adds another layer of intrigue to Victoria's complex geological history. As we delve into this rich history, we will uncover more fascinating insights about the extraordinary transformations Victoria's landscape has undergone over millions of years. It's a story that's still being written, one discovery at a time. Thanks for watching.
Many have asked the question, is there gold under Melbourne? Yes. Yes, there is. Melbourne is basically the city of traffic and basalt. That's really all you see, minus the few places where sedimentary rocks peek their heads out. In fact, close to half the state of Victoria is covered in basalt. This is very recent though, with these eruptions occurring only within the past 7 million years. Prior to that, Victoria was a very boring place, if you're a fan of change that is. It basically sat more or less undisturbed in a geological sense for tens to hundreds of millions of years, and in that time, you can bet that gold flowed through the ancient land that would one day host the city of Melbourne. In this video, I'm going to discuss the goldfield that definitely exists under Melbourne, and it's been found too. The real issue isn't whether or not gold exists, it's whether or not you can access it, and more importantly, whether or not it's payable. The earliest accounts of gold existing in Victoria occurred during the 1840s. Shepherds and farm labourers would stumble across nuggets inside waterways, or they'd see visible gold inside quartz rocks. Mining was illegal back then, as gold and all metals were the property of the Crown, and the discovery of gold was also actively discouraged. But as always, there's people who gave a big middle finger to the rules, and one of the first was a fella known as Gum the Gold Hunter. He lived in a hut in Plenty Ranges, now known as the Warrenheip goldfields, and he'd be doing his thing over there. And along with this, a secretive underground black market trade existed, and many shepherds and farm labourers would sell it to jewellers in Melbourne on the hush-hush. Then, in the 1850s, New South Wales discovered it had gold, and Victoria's hand was finally forced. They had to find and release their own gold discoveries in order to not lose all of their skilled labour to the rushes that were occurring in New South Wales. And it was around this time that gold would be found in Melbourne. Here's the issue though. One of the first regulations that existed back during those early days, which governed gold mining in Victoria, stated that mining could not take place within 1 mile of a settlement or station that was in existence prior to the discovery of gold. And thus, this made any mining illegal, as Melbourne and its surrounding suburbs already existed back then. And this is more or less what halted the real discovery here. The first discovery of gold, near Melbourne CBD, was thought to be a fluke. A labourer in Richmond discovered gold whilst digging a post hole. Now, many stories were complete furphies, but some of them were legitimate finds, and there is no question about it, there was definitely gold under Melbourne. Take this article from the Argus, posted on Monday the 28th of July in 1851. Gold was found in the soil at the western end of Burke Street, and the guy who discovered it? Well, it's the same fella who claimed to have been the discoverer of the Bendigo goldfield. Then, in August of 1851, in a lane in Lonsdale Street between Exhibition and Spring Street, a white rock fragment was poking out of the ground, and two children came across it and dug it out with a stick. They saw a quote, pretty thing in it, and they showed their mother, who then took it to a jeweller for examination. A man named Mr. Crate in Swanston Street tested it, weighed it, and pronounced it to be a pure specimen weighing just over half an ounce. Now you can just imagine how many people walked past this quartz rock that had half an ounce of gold inside it without realising. As previously mentioned, mining was banned in Melbourne, but people still dug in spite of the law. Several folks from the localities where discoveries were made set to work and found, at a depth of only 18 inches from the surface, a bed of dark quartz, which generated massive excitement, which was then never mentioned or spoken about again, and thus no one knows what the heck happened here, but suppression is a possibility, and the most probable culprit to this fizzling out, of course. Regardless of this, things still began to get a little out of control. Lonsdale Street and the northern end of town began to change to something more resembling a gold rush city. Claims of gold finds were continually made. One of gold being found at Lonsdale Street was made near the old Treasury building, by a digger that had worked the grounds in Ballarat. He spotted the same bluish clay that he had encountered in Ballarat, and, out of curiosity, tested a few lumps of it and found specks of gold inside. This sparked a rush, and several parties began to work with pick and shovel, and one man was witnessed to have extracted a nugget that was the size of a large pea. A reporter that was on the scene concluded that there is no doubt whatsoever that there is gold there and in large abundance. On the 2nd of September in 1853, gold had been discovered on Emerald Hill in South Melbourne. Half a dozen small nuggets, with the largest being about half the size of a small pea, were presented to a reporter for the Argus. At one time, about 100 persons had assembled there, and our reporter saw and heard of in the possession of various persons as many as about 50 nuggets. Besides this, he saw gold in all various stages of washing. Several applications to get the right to dig were made, but all were met with stiff refusal. Eventually, the law cracked down and stopped any further digging here. It seems like this area of Melbourne is quite auriferous, as at the west end of Lonsdale Street, as you approach Flagstaff Hill, another find would be made. One find in 1856 was responsible for breaking up a church service, and by the time it was over 100 of the parishioners were out digging using whatever implements they had on them to prize specks of gold from the familiar blue-tinged clay. By the early 1860s, gold had been found in the footpath of Hoddle Street, at Paran Railway Station, on Batman's Hill, which is now the site of Spencer Street Station, and at Templestowe and Heidelberg. But these finds didn't raise as much of a sensation anymore. A man offered a geological explanation in 1862 for the presence of gold in Melbourne and its suburbs. He noticed the absence of gravel in Melbourne, and by studying rail and road cuttings in Paran and Richmond, he predicted that a large deep lead ran through Melbourne to the bay, and he proposed prospecting under the basalt and adjacent to the high ground furthest from the present-day Yarra River. In later decades, boreholes were sunk to find this, but nothing really ever came up. So where's the gold coming from? Well, everywhere. The man who offered an explanation for the presence of gold was right to some extent. There sure are plenty of rivers that were buried in the past 7 million years as volcanic eruptions roared forth and oozed lava time and time again, burying pretty much everything in its way. But what the man didn't realise is that, well, Melbourne is a goldfield, as much as any other part of Victoria is. It was as much involved in the cycles of tectonic collision and later mineralization as all of the other parts of Victoria are. It's just all under basalt. And this is cool, but it also sucks, because the basalt is deep and tough as anything to break through. So how were shallow deposits found? Well, if you look at the locations where they were actually found and overlay a geological map, you can see a bit of a trend. And that is, they were all pretty much found in areas with either no basaltic cover or with very little. It's not so much that Melbourne had the old Yarra making it auriferous, as it is the fact that Melbourne is itself auriferous. And there are many examples where the strange gold mines that dot Melbourne, of which there are a few by the way, were all found in areas where basaltic cover was non-existent or very shallow in its deposition. So really, the gold that was found in the Silurian geological area that was outcropping in Melbourne, which is over 440 million years old, and was deposited around the time that Victoria began to become as gold enriched as it would turn out to be. So as you can see, we have the typical basaltic cover that's seen around much of Victoria here, and the tullamarine basalt flow in orange over here. The purple though is the Silurian Melbourne Formation, and if there's mineralization and quartz veins that shot through this formation, like it did with the Castlemaine group that we see in the richest goldfields from Ballarat to Bendigo, then it's this sedimentary layer that would host it. And as you can see, very little of this purple layer exists in Melbourne, as the vast majority of it is covered in basaltic flows. That is, until we go a little east, and what do you know? There's the Warrenheip goldfields. Just another example of the fact that these deposits were always here, and are just a natural part of the land like they are in Ballarat, Castlemaine or Bendigo. It's just covered in that cheeky basalt. So grab a shovel and dig your nice little garden or your freshly mowed turf in your backyard in Melbourne. You might just find some good gold right underneath ya. It's worth a go at the very least. Thanks for watching. The Devonian era was an incredibly chaotic time for southeastern Australia. It was by far the most volcanically active and explosive that this land has ever been. Massive calderas left over from the many ultra-Plinian and supervolcanic eruptions that occurred here at this point in time are dotted all throughout the state, many of which are still visible today, existing largely in the eastern part of the state with a few notable exceptions. This part of the continent has gone from being a deep ocean 600 million years ago to being thrust up to dry land after numerous tectonic collisions occurred here over the course of about 300 million years. Along with the many subduction events were numerous episodes of rifting too, and both of these situations created a perfect setting for both supervolcanoes and for extremely large explosive volcanoes to form, and that's exactly what happened here. Unfortunately, I have to break this episode up into two parts. This episode will focus on the late Devonian volcanic eruptions, whose fuel was derived from subduction-related processes from tectonic collisions and subsequent orogenies that occurred. In part 2, things turn up a notch in intensity, and the volcanism that we see here occurred primarily in the early Devonian, at a location in Victoria where a rift formed and the land split apart, allowing vast quantities of magma to exploit this weakness and rise up from the mantle, forming literally dozens of massive volcanic calderas that we can see in present day. So in this series, we're going to take a look at Victoria's largest volcanic structures. I'll show you how I discover them and what tools I use to do so. Victoria is literally dotted with dozens of massive calderas. We have volcanoes here ranging from your ultra-Plinian forming eruption that could have released anywhere from 100 to 600 plus kilometers cubed of material to the true beasts that release 1000 plus kilometers cubed worth of volcanic material during singular eruptions. Victoria is a truly fascinating state. I'm definitely going to miss out on a few calderas as I'm still discovering new ones today, and I actually just found one a few days ago after looking at this fault map and noticing a circular feature whilst creating the last video on how New Zealand creates earthquakes in Australia. Cheeky plug, but the link to that video is down below in the description. Unfortunately, very little published and easily available research exists on most of these volcanic areas. Like literally, the amount of studies that have been released to the public or just Googleable in general are absolutely none for most of these calderas, which makes me sad inside. But that is also why I continue to discover volcanic calderas on my own, which is a kind of fun hobby in a way, because there's nothing I enjoy more than discovering new calderas and kind of nerding out on how powerful it must have been when it had erupted. The first supervolcanic caldera that we are going to look at is the Cerberine caldera. Unlike the following volcanic calderas that we're going to look at after this, there is actually good research available to the public on this caldera. The volcanic entity that spawned this eruption and several other large ones is known as the Marysville Igneous Complex. Just south of the Cerberean caldera exists another moderately large caldera called the Archeron caldera, which shared the same magma chamber and was a smaller version of it. The Cerberean caldera released at least 1,000 kilometers cubed worth of material and was definitely a VEI 8 on the Volcanic Explosivity Index, meaning yes, it was a supervolcanic eruption of tremendous proportion, with it more than likely having significant planet-altering impacts in the form of a volcanic winter among other things. And some Australian geologists think it might have been responsible for, or at the very least contributed to, the Devonian extinction event. This cauldron erupted more than once, so it's possible it's covering past supervolcanic eruptions since layers of ignimbrite from differing eruptions do exist here. Before we go on, it's worth explaining what ignimbrite is for any of our new viewers so they can conceptualize and understand what I mean by it during the dozen or more times that I'll mention it in this video. When explosive volcanoes erupt, they release a pyroclastic flow. This is essentially a very dense, semi-molten cloud of death in the form of noxious gases and volcanic particles that hugs the ground when it's released, and it travels at ridiculous speeds of up to 700 kilometers per hour, which is 435 miles per hour for you Yanks out there. It exists at a temperature so hot it will instantly bake you to crispy nothingness, with most of these pyroclastic flows being up to 1000 degrees Celsius, which is a ridiculous 1800 degrees Fahrenheit. When pyroclastic flows cool down and solidify into rock, they are called ignimbrites, which, to further define, Google tells me is a
volcanic rock consisting essentially of pumice fragments formed by the consolidation of material deposited by pyroclastic flows.
Thanks, Google. When supervolcanoes erupt, they release a truly unbelievable amount of ignimbrite. The pyroclastic flows are just beyond imaginable. So the last mega eruption that occurred at the Cerberean caldera did so around 365 million years ago, and the original caldera rim size was 27 kilometers in diameter, but erosion has since whittled that down. With that being said though, you can still make it out on Google Maps when using satellite view, which is just incredible. The ignimbrite flows that were released buried the surrounding areas in up to 300 meters worth of ignimbritic rhyolite, and following this, a second tough layer was released which buried the surrounding land in 900 meters worth of rhyodacite. When we switch to the geological map, you can very clearly make out an outline that will become familiar to you as you continue to watch this video. This is how normal faults look in Victoria, a roughly east to west compression line that was created from the numerous subduction events that occurred here. These faults are basically the remains of the land being folded and compressed to the point of breaking and snapping apart when this land was aggressively uplifted from a deep sea. Now, this is a ring dike. Notice just how different these are to vertical subduction related faults. Oh, and those lines that you see through them are called ring faults. This is a very common thing to see when very large supervolcanic or extremely large volcanic eruptions occur. They absolutely decimate the ground to such an extent that they fault it when the caldera collapses in upon itself after sufficient magma has drained from the magma chamber. And it produces these ring-like shapes, and the faults can serve as conduits for future magma to rise up from. When the Cerberean caldera collapse occurred, it dropped between 1 to 2 kilometers into the earth, which is kind of unbelievable to think about. Now, just south of the Cerberean caldera, we have the Archeron caldera. Similar to the Cerberean one, we have a ring dike with faults striking through it. The tuff layer it released is predominantly rhyodacite, and this occurred around the same time as the Cerberean super eruption, since it shared the same magmatic source. Now check out what happens when we click on the magnetics. Bam! Suddenly we can see the outline of both calderas. Isn't that truly incredible? It drowns out all of the uninteresting stuff, leaving only this behind. This isn't always the case though with all calderas, but with these two it's really striking just how clear we can see the features. Moving on, and now we're heading just a little north of the Cerberean caldera. This is my most recent discovery. Upon taking a closer look, I found a few ignimbrite tuff layers here that were released during the late Devonian. The Ryans Creek ignimbrite and the Toombalup ignimbrite are the two predominant tuff layers that we see outcropping on the surface. But there exists at least 2 other felsic eruptions that occurred here, with one of these spawning another ignimbrite layer called the Hollands Creek ignimbrite, which released a layer that was 300 meters deep. My suspicions for this place turned out to be correct. It's known as the Tolmi Igneous Complex, a subaerial caldera. Subaerial basically means when this eruption occurred, it did so above water and not in a submerged state. A little side note, we also have the Whitlands volcanic group existing here, and this is a repeating theme that will occur along with the many other volcanic structures that we will look at. It is a much more recently erupted basaltic lava flow that occurred here within the past 50 million years, and the fault conduits that it used to ascend were probably the same faults that were created during these massive explosive eruptions, which I personally find interesting and fascinating, but I digress. On the magnetics, we don't see much, which is misleading, true? I mean, clearly ignimbrite was released here on a massive scale, so what gives? Well, as always, geology is all about understanding that there is never a one-size-fits-all situation and things always differ. Because when we look at the fault map, we can very clearly see a semi-ring dike feature along with ring faults. Perhaps eruptions that followed hit what lay here from magnetics or covered it up, but the faults don't lie. It's very possible that this was as large or even larger than the Cerberian caldera just based on the size of this structure. Unfortunately, like I previously mentioned, I find it extremely difficult to find proper studies on Victorian volcanoes. If anyone knows where I can find this info, please do let me know. This is the best information that I could find for most of the volcanic calderas. It was previously known as the Rose River Volcanics, and the Ryan's Creek ignimbrite covered the land in a layer that is a ridiculous 450 meters deep. The accompanying Toombalup ignimbrite was even larger. It released a layer that is 700 meters deep. If I was to guess the shape of the calderas, I would guess that this would be it. With that being said though, 2 other major eruptions did also occur here, so I could be wrong. I just wanted to say, if this video gets enough likes, I'm going to go in person to each one of these locations to do a further deep dive into them and to create individual episodes based on them. And I'll also shoot some drone footage so that we can marvel at the size of these calderas and see whether or not we can identify it visually in present day. So if that's something you'd genuinely like to see, please leave a like on the video to let me know, as I'd really be keen to do a full series of videos where we go from one supervolcanic location to the next. The next caldera we have is a bit of a weird one. It's weird because it doesn't look like a caldera at all, anymore. Nowadays, it exists as a mountain. The Dandenong Ranges Igneous Complex, also known as the Dandenong Ranges or more affectionately as the Nongs, is an area that all Victorians have heard of. The mountain can be seen from almost all corners of the surrounding Melbourne CBD and the outlying suburbs. This mountain isn't really a mountain in the traditional sense, rather the extremely erosion-resistant volcanic material has remained and the surrounding land has eroded and whittled down around it over the course of its 360-odd million year long life, leaving this massive mountain in present day, which is basically the remains of a now eroded caldera. When we switch to the geological map, we can see that this entire mountain is actually comprised of 4 ignimbrite flows of varying amounts. We have one rhyolite eruption that released the cold stream rhyolite, whose depth isn't stated on the stratigraphic units database, and along with this it also released 3 rhyodacite eruptions. The Ferny Creek eruption released a layer that buried the surrounding earth in 400 meters of rhyodacite ignimbrite, and the Kalorama and Mount Evelyn rhyodacite tuff layers were both at 300 meters in depth. Even though this material is erosion resistant, it has eroded quite a bit, as you can see by these very rounded shapes, and by the fact that magnetics aren't too strong here at all. And just like before, alongside these massive ignimbrite flows exists a much more recent lava flow that more than likely ascended from the very same fault lines created by these massive eruptions, and it itself is known as the Monbulk volcanic group, and it released extremely runny basaltic lava flows which would have created vast lava rivers that would have flowed in the surrounding land. In present day, the caldera or calderas that were created by these volcanic eruptions is less obvious, primarily because everything has eroded to such a great degree that though there does exist a ring dike-like shape here, it's much harder to make out because the area that this exists in hasn't really experienced much uplift compared to the other two igneous complexes that we just looked at, which in present day exist within the Alps, and the Alps are still growing at a rate of 76 meters every million years or so in present day, and the Dandenongs exist just outside this range. Since we've been discussing Mount Dandenong, I might as well jump to the next volcanic structure that is equally as well known and is very similar to Mount Dandenong in the fact that it is also far away from the Alps, and because of this, it exists as a mountain amongst much flatter land that has eroded around it. It was this exact volcanic structure that made me want to create the content that I make today on this channel over 4 years ago when I first set out to create it, so I hold a very deep reverence for it. Mount Macedon is known formally as the Macedon Igneous Complex, and it is comprised of 2 ignimbrite flows and 1 intrusive event that created the Baringo granodiorite in present day. Just like all the volcanics discussed thus far, this occurred in the late Devonian, and the 2 tuff layers here are known as the Willemy Gong Gong and Heskett ignimbrite flows. The Willemy Gong Gong ignimbrite is comprised of rhyodacite, and the maximum depth of it is unknown because of the extreme amounts of erosion that has taken place in the past 360 odd million years since it formed, but at least 400 meters of it exists today. The Heskett ignimbrite flows underlies the Willemy Gong Gong ignimbrite, and it has no information on the depth documented, which is extremely disappointing. The magnetics do show a very faded ring-shaped outline, and just like before, all around Mount Macedon are younger basalt flows, including some that occurred in the middle of the mountain itself, meaning this basalt rose up amongst all the ignimbrite rocks, melted some of them, and erupted onto the surface as trachyte lava en masse in and around the entire mountain. After Macedon, we head back east to our last volcano of this episode, the Violet Town volcanic group, comprising of 1 singular rhyodacite ignimbrite flow with a depth that I can't seem to find. This volcanic complex was quite hard to find information on. It erupted 373 million years ago, and the present day outcrop is very heavily eroded. When looked at through magnetics, we barely see any signs of a caldera. But if we look at it through a new feature, which I haven't showed you yet, called gravity, we can see something a little different. If I was to guess, based on this scan and the 1 circular fault that we've mapped so far, I'd say it might have had a structure like this. But this is a big shot in the dark, and this is pretty big, but it is possible, and along with this volcanic feature are massive amounts of intrusives that followed. So this pretty much concludes the late Devonian eruptions of significance that are visible in present day. If I missed any areas, please do let me know. In part 2, things turn up quite a notch. We go back in time from the late Devonian to the early Devonian when Victoria began to be rifted apart. This rift zone created a much more aggressive form of volcanism than the subduction-related calderas that we covered in this episode. And by aggressive, I really do mean aggressive. And along with this, in the next episode, we are going to use a lot more gravity scans, whilst continuing to rely on magnetics, geological maps, and fault maps. In the present-day town of Buchan, in Victoria's far east, we see signs all over the place of the turbulent history that occurred here. The Devonian era was a time of marked chaos and destructivity for the land of southeastern Australia. When the Buchan Rift formed, it ushered in some of the most impressive and powerful volcanoes that Victoria has ever seen. Ancient limestone caves are dotted all throughout the land, from the ancient coral reefs that once existed here. At first, the land fractured only a little, but with time, it would continue to rift and split apart, forming the large rift valley that we can clearly see today. The Buchan Rift is very easy to make out on maps, but it's on the magnetics and gravity where it really stands out. Here we can see the rift borders and the massive amount of varying eruptions that took place here in the form of the many circular features that exist. I mean, it's literally filled with calderas, both small and large. When the rifting occurred here, vast, and I really do mean vast, amounts of magma was able to easily intrude the crust as it rose up from the mantle to fill the voids that were being created by the rifting here. And in doing so, the extremely hot basaltic magma began to melt the older silica-rich volcanic rocks that were all around it. changing the chemistry and raising the level of silica, leading to the massive explosive eruptions that have occurred all over the place. On top of this, we have a number of areas around the rift where rhyolitic lava was extruded en masse, not in explosive eruptions, but in lava flows, and the only time that this happens is after a massive eruption occurs, because a massive eruption releases so much of the volatile gases and pressure that was contained in the magma that it allows what is left over to rise up and extrude after the eruption, even if what is left is this extremely thick rhyolitic magma. It is extremely rare to see this magma flow as lava, and so this event really only ever occurs after a massive violent eruption has ended. Now let's get into the actual layers of ignimbrite that exist here. Geologists put the ignimbrite flows that occurred here under one big group, known as the Snowy River Volcanic System, and take a look at how big it is. So, as you can probably deduce from seeing this, the first thing to understand about this area is it's an absolute mindfuck. There are so many ignimbrite flows, at least 36, and these weren't little explosions, these were massive eruptions that released layer after layer of pyroclastic flows from all over the place time and time again. And many of these ignimbrite flows cover up past calderas and make the landscape incredibly convoluted and confusing to read. All up, the Snowy River Volcanics are divided into 18 subgroups, of which at least 36 ignimbrite layers exist, along with several rhyolitic lava flows and differing shallow intrusives. There are numerous eruption points spanning from north to south, creating dozens of calderas, many of which would be buried by each successive eruption that followed, making the interpretation of this land incredibly difficult. One thing to keep in mind is this map that I'm using will sometimes say Snowy River Volcanics, and other times it will actually list the ignimbrite layer, but all layers associated with this rift are associated with the Snowy River Volcanics. I don't know why it does that, but it unfortunately just does. A lot of this video will be my own speculation and theories regarding what could be possible calderas, and it is not official by any means. Geologists have classified this area into the differing outcropping tuff layers, and no research that I'm aware of has really been focused on mapping out the calderas, so we're going to give it a go using magnetics and gravity and seeing if they match up with the corresponding tuff layers. Do keep in mind that because these formed while the rift was active, they could be more spread apart than they originally were when they formed. Before we get started, if you'd like to see a follow-up episode of this where I go to the Buchan Rift in person and shoot some drone footage as well as explore the cave system and volcanic calderas, please click the like button. Let's get started. Thankfully, we can easily see the most well-known caldera when viewed under the magnetics. This part of the caldera is particularly amazing though because the erosion in the center of it has just started revealing the intrusive rocks that exist underneath the massive caldera that were at one point in time fueling the magma chamber. The Warrenheip flat granite formed in the Silurian, and the tuff layer above it is the Snowy River Volcanics. I think there are actually two calderas here, a larger one and possibly a smaller one, and it's surrounded by a tiny amount of basalt flows. Up north, we have this beast that I actually think is 8 calderas spaced right near each other, like this. The reason I say this, aside from the shapes and the magnetics, is because multiple tuff layers exist in this one area overlapping one another. We have the White Monkey Volcanic Group, the Bowen Track, Douglas, Statham, and Minchin Ignimbrite, along with the Mackeson Spur Tuff, and another separate Snowy River rhyolite layer, and quite possibly the Dedic Rhyodacite layer. By now, you probably understand why I said this area is super confusing. Well, that's nothing, because when we move a little west, now we have a mass of recent basaltic lava flows that occurred here within the past 50 million years, and these are actively hiding tuff layers, but let's try our best to work this out. We know something big happened here. Aside from the magnetics showing large circular features, we have the Dingo Hill lava flows, which are ancient rhyolite lava flows that occurred after a massive caldera-forming eruption happened here, which I assumed was related to this caldera, which actually looks to have another smaller caldera within it, with another looking to exist just southwest of that one. It's hard to know which layer is associated with this, But something of this size might have released the very widespread Galantipi ignimbrite, or Galantipi ignimbrite, I don't know how to pronounce it. It's also possible the caldera actually looked like this, and that it released either the aforementioned ignimbrite or the Glenshiel or Statham ignimbrite. Moving a little north, and we have an outline, or possibly two, that appear to look like much older ring dikes that have been covered up by preceding tuff layers, and this will be a reoccurring theme unfortunately, as the only eroded bit underneath this massive Statham ignimbrite layer only states that it is a snowy river rhyolite. So I have no way of identifying this tuff layer that is underneath it, and that might be associated with these caldera-like formations that we see. Now, all throughout here, you'll see smaller circular structures, which definitely could be older, smaller calderas that formed, like here. But for the sake of both yours and my time, I'm going to try to stick with the larger eruptions only, but every now and then the maps will show dots in smaller features, showing you an area I think might be a smaller caldera. Heading north again, and we see these faded protrusions. This definitely looks like ring dikes to me, either one or two, with what looks like a third and fourth existing just a little north of them. Now, some of the corresponding tuff layers might be buried and are no longer exposed, but some that are the Wombago subgroup, the Black Mountain and Black Satin ignimbrite layers, the Wolgolmerang volcaniclastics, and like always, the Snowy River volcanic group. Moving south now, and we have this circular feature here, along with smaller ring shapes from what looks to be another eruption. These look to be related to the Glenshiel ignimbrite and Trendale formation, both of which have been covered up heavily by preceding eruptions, and they barely outcrop today. And here we have some of the Buchan caves and the associated limestone, which you can see is all over the place from the coral reefs that once existed here when this area was sea 400 million years ago. Now things get a little complicated here. There are circular features which look to be calderas, along with other more subtle features, which hint to the possibility of the existence of one, like this one here, which is an active ignimbrite field made up of the Tolok Ard, Mooncan and Dataka ignimbrite layers, which has the Little River subgroup outcropping in the middle of it. I mean, something big definitely happened here, because we also have the Raymond Falls rhyolite lava flow that occurred post-caldera collapse. So this outline is telling. But what about this incredibly thick line of completely different ignimbrite layers that only exist in this area? Are these possible caldera outlines? Was the volcanic activity here so immense that it built this area up, or was it uplifted long after the volcanoes died? I'm not sure, but it's only here where I can seem to find these tuff layers, which are the Dead Cattle Gully, Dunalik, Doyle Gully, Biman, Plum Gully, Mount Dawson, McRae's, Carson Creek, and Lookout Top ignimbrite layers, so it looks like a lot happened here. There also might have been one, but more likely two, and possibly even three calderas here. West of that, we have another few circular protrusions, starting with the smaller one at the top. It looks to be associated with the Woolshed Creek ignimbrite, and as we move south, we can see two rather large circular features here and here. These look to be associated with the Yellow Waterholes, Dix Creek, Gordon Creek, and Frying Pan Creek ignimbrite layers. This was definitely an area of pronounced volcanism, as we see the Dinner Hill Gap rhyolitic lava flows here, which released a very thick and large amount of rhyolite lava. Now moving on, and a little to the south of this, and we have a tuff layer that I can only find around this hard to make out circular feature. The Jalung ignimbrite layer just barely outcrops over here, and on the magnetics, it looks like there's possibly 2, 3, or maybe even 4 overlapping calderas here. One thing that might surprise you is that this little caldera looking shape here is actually the lava dome that was formed by the rhyolitic lava flows of the Raymond Falls layer. The faulting here shows a ring dike-like shape to it, and we have the Fluke Knob, Canny, Rankin Road, and Tomato Creek ignimbrite layers here. Around here is also these castor oil lava layers. There are 2 of them, a rhyolitic version and a mafic version of it, that were released around the same time. So that's the rundown on this massive rift zone. Now let's move on and head west just a little out of the Rift Valley to this beautiful circular feature that is the most visually striking feature that we will see all night when viewed under a fault map. This is probably the most perfect ring dike that I've ever seen in Victoria. I mean, come on, you can't beat this. The magnetics aren't as perfect as the fault map, but they are still almost completely circular. This eruption released the fainting range ignimbrite tuff layer, which contains rare quartz phenocrysts within it. I couldn't find the size of this tuff layer, but there does exist another alongside it, known as the Slater ignimbrite, whose depth I also couldn't find to no one's surprise by this point. The actual system itself is known as the Mount Elizabeth Caldera Complex. So we're down to our final few outliers that occurred in the early Devonian. Just west of the rift zone, we have these layers of ignimbrite, one of which might be familiar. So we have the Carriage Range, Tin Pot, and Quindalup ignimbrite, as well as, what is this? The Snowy River Volcanics. That's right, as you can see, this massive amount of horizontal faults allowed magma from the rift zone to also erupt here by travelling through these faults. The eruptions were far less frequent here though, and we can barely make out the caldera shapes, but if I was to guess, I'd say this is how it looked. Along with this, we have the Sapper Nose Rhyolite member, which started life as a submarine lava flow, along with the Thorcadan Volcanics, and this actually links all the way through to the rift itself, showing the correlation and direction of magma travel. As we move a little further north, we can see the outlines of the small caldera that released the Besford ignimbrite layer, and after this, we come to our final few possible caldera locations. The magnetics here are quite clear, this big ring shape with another one or possibly two calderas existing just north of it, which looks to be associated with the Mitter, Shiva's Spur, Larson Creek, and Murtagh Creek ignimbrite layers. We have some clear ring dike outlines on the faults here, and the magnetics are really the only way to identify what seems to be these very faded caldera-shaped outlines here. And just north of this, we have our final caldera. This mess of heavily faulted ignimbrites is known as the Jemba ignimbrite. So around the time that these volcanic systems were alive, another system was active in Western Victoria, and that is a topic for another video as it released highly precious rhyolite lava flows that are filled with gems and geodes that exist in present day, and I think that makes it worthy of a video of its own. So after this, we had a tiny wave of volcanism in the Middle Devonian during the orogeny that occurred, but things wouldn't really pick up until the orogeny reached its end, when, in the late Devonian, the largest caldera-forming eruptions to exist in Victoria occurred, and we've already covered them in part 1. A turbulent and chaotic history hides beneath the soil in Western Victoria, and it's hidden remarkably well beneath the recently deposited sedimentary layers of the Otway and Murray Basin. We see only small outcrops of the ancient landscape that this area once existed as, back when it was a much more chaotic place. Volcanoes existed here en masse, from large stratovolcanoes to massive circular depressions known as calderas, which are left over after the largest and most explosive volcanoes erupt, with a few minor exceptions to that rule. But eruptions of staggering size occurred in this area, and tectonic collisions occurred time and time again, and within a period of about 200 million years, Victoria was slowly buckled and thrust up from the deep ocean floor episodically, with each part of the state slowly being raised one piece at a time, starting from the west and stretching all the way to the far east. One area in particular though is truly interesting. It's an outcropping of rhyolitic lava that was erupted forth after a massive eruption occurred here, but when this lava solidified, the formation of something truly precious and unique occurred here. You can find an abundance of geodes here, which are these incredibly beautiful spherical rocks that contain hollow cavities lined with crystals, along with smoky quartz crystals, also known as the Morella crystals. The presence of both the geodes and the smoky quartz crystals have a fascinating origin story, because their existence is tied with several huge explosive caldera-forming volcanic eruptions that occurred in the early Devonian. These eruptions were quite large in size, and they released a vast amount of pyroclastic flows, depositing massive ignimbrite fields. And along with this, rhyolitic lava was also released after these eruptions occurred, which, if you've watched our last video on Victoria's Rift Zone and the associated massive eruptions that occurred in the eastern part of Victoria during the early Devonian, cheeky plug, but the link to that is in the description below, you'll know that rhyolitic lava in this scenario is only extruded and released after a massive eruption has occurred, which is necessary to depressurize the magma chamber to such an extent that this thick, viscous magma is able to be released in its lava state, which is something that is quite rare to find rhyolite in. This thick lava is basically the magma that was left over in the magma chamber after the massive eruption occurred here, and so it continues to slowly rise to the surface and leak out following this, which is a trait that is rare for this magma. It is normally only associated with explosive eruptions, not gentle, effusive ones like these were. Because of this, the geodes and gemstones here are unique and some are truly marvelous to glance at. The decomposing layer of rhyolite that these precious and semi-precious gemstones and geodes exist within are only exposed through weathered areas, or in areas that have eroded slightly around them. So these mainly occur as a small hill-like outcrop, or in areas of natural drainage, and thus finding the source of the volcanoes that released both the rhyolitic ignimbrite layers and the associated lava flows has been impossible. Well, maybe not. I might have discovered a caldera or 2, or 10, or more, as you'll see in this video. I use magnetics to peek beneath the sedimentary layers, so this video is also going to look beneath the Murray and Otway basins to try and discover some other possible calderas that are either related to or occurred around the same time as the release of the Rocklands volcanic group, which is the group that encompasses the Morella gemfields. And we'll also take a look at the many associated ignimbrite layers that occurred in this area. The treasured smoky quartz crystals and geodes have been highly sought after since the 1960s, when this gemfield was first discovered. Good specimens could be found near the surface back then, but nowadays, holes are dug down to depths approaching 6 meters to find the really valuable specimens. But for those who aren't as fussy and don't mind smaller geodes or loose smoky quartz crystal clusters, 2 meters deep is usually the depth required to fulfill this desire, and it's legally allowed to be done in this area. I would love to head out to this gemfield one day to make a future video, and try to dig down and find some good geodes and smoky quartz crystal specimens. So if this is something you'd like to see, please let me know by hitting the like button, and I'll add it to the list of videos that I'm planning on doing in the near future. The Rocklands volcanic group was released amongst a much older volcanic arc that was only recently discovered, known as the Staveley Arc, and I made a video on this, so if you'd like to see it, it's in the description below. But this ancient volcanic arc marked the first beginnings of Victoria's inception when it was thrust up from a deep ocean to dry land, and it, along with the much later released Rocklands rhyolite lava flows, have been heavily covered up by the more recent sediments related to the 2 aforementioned basins. It's only by using magnetics that we can distinguish what exists beneath these deep sedimentary basins. And as you can see, we have just uncovered the deeply buried Staveley volcanic arc, and it is now in full view. So the Rocklands volcanic group consists of 2 differing layers, the rhyolite lava and the intermediate lava flows. But what's striking is just how widespread the rhyolitic version of this lava is. It's existing much farther south than just the Morella gemfields, all the way past Wannon, with another section exposed at Bocara. After seeing how vast the rhyolite lava flows were, I knew something very, very big happened here, and this stretched way beyond the gemstones and geodes. There is a possible supervolcanic scale event lurking beneath the sands and sediments, and if not, then numerous large VEI-7 eruptions definitely did occur here, numerous times. These lava flows are just too vast in my opinion. So along with the lava flows we've just covered, we have all of these ignimbrite layers all over the place, many of which were a precursor to the lava flows that would follow the largest and most explosive eruptions. It's worth mentioning that the Rocklands volcanic group itself is composed of numerous differing eruptions, all of which have been lumped together into this group, which I assume is for the sake of convenience, and understandably so, because look at this area, it's an absolute mess. But we also have all of these independently named ignimbrite layers, which are the solidified remains of the once massive and scorching pyroclastic flow layers that were released by the now hidden volcanic structures dotted all around here. In this area, we have the Negretta, Gaddam, Glendinning, Cadden, Yatnat, and unsurprisingly, the Morella ignimbrite. Now, this is where things get a little fun. As always, this is all my speculation regarding possible calderas, but I'll offer my arguments and let's theorize a little. Take a look at this ignimbrite layer. The Glendinning ignimbrite layer stretches quite far, but at this location, where this tiny bit outcrops, we see something that amazed me. Look at this. When we switch to magnetics, we see these circular shapes, and there are many of them. I really do believe this caldera, or one of the others that are near it, released this ignimbrite layer, as it's the closest layer that exists to these structures. The possible caldera is completely covered up by the alluvium that's related to the eroding of this part of the Grampians. When we move south to Morella, we have this rhyolite lava that is associated with the gemfield itself. Rhyolite lava doesn't normally travel far though, so it's common that it will be released right above or close to the caldera that allowed it to extrude, right? Well, the magnetics might corroborate that claim. We have what looks like numerous volcanic eruptions of tremendous scale occurring here. I see 3, 4, or possibly 5 caldera-looking circles crossing over one another that are both small and large in size here, but what really strikes me is this large ring here, which might even be this. And look at that near perfect circular feature just southwest of this, here. So now we know why this gemfield exists. Something massive took place here. This makes me wonder if the rift zone in Victoria and the rhyolite lava flows that exist there contain geodes or gemstones of a similar quality. Maybe. But I believe in my heart of hearts that these are a number of massive calderas that released many of the ignimbrite layers that I have already mentioned. Now, a little south of this, and we have the Mount Mackeson's Rocklands volcanic group rhyolite lava. And under the magnetics, surprise surprise, we have a massive ring shape here. Like massive. There's a possibility it was this big, with another eruption inside of it. I see 3 or 4 large circular features here, all of which could be large calderas. Now, this is a reoccurring theme. In the southernmost section that outcrops over around Wannon, we have several distinct ring-looking shapes beneath Wannon, Ballarat, and Hensley Park. These look freakishly big, honestly, like I'm not even trying to embellish this. After all the magnetics that I've looked at, this looks like a massive supervolcanic scale event occurring here, or possibly numerous ones. But not everything is seemingly this obvious. In this little outcrop of rhyolite, the magnetics do not seem clear here. I mean, look at this massive amount of volcanic rock, which I assume is primarily intrusive. It looks like one major ring might exist here, along with several other smaller calderas. I can't help but wonder whether or not those little dots in the far north are actually smaller stratovolcanoes that have been buried, and maybe this mass of volcanic rock was once a churning magma chamber that fed it, and are now the solidified intrusive rocks that we see here. But when we move east to Vassy, we see the same reoccurring theme, rhyolite layers, along with some intermediate lava flows this time. Nevertheless, under the magnetics, we have what appears to be several large calderas here. Beginning from the bottom, we have what appears to be 2 large calderas, along with 2 or more smaller ones north of that. And north of this, we have what appears to be another 1 or 2 very large calderas, alongside 1 or 2 lesser calderas. Just west of this, we have another rocklands layer, and bam, another 1 or 2 caldera-looking shapes, with a possible smaller 2 or more just north of it. So these shapes look like calderas too, but we have no outcrops. And if we move northeast, we see this massive array of rings. It looks like one supervolcanic eruption after another occurred here. We have what looks to be caldera after caldera, seemingly like a hotspot similar to Yellowstone was lurking beneath here. No outcrop exists, but come on, I'd bet money that these are calderas. So that's the fascinating and complicated story of this glorious present-day gemfield. It was formed by spectacular and devastating volcanic events that are at a scale of explosivity that is difficult to imagine in present day. It's a shame that the ancient land that this place once existed as has become buried beneath the sands and sediments of time. But at least we have these incredible tools to try to unearth some of Earth's hidden secrets. I believe this land would have been dotted with massive calderas, which would have erupted amongst an ancient volcanic arc that would have most likely still been standing when these gigantic eruptions occurred. Nowadays, the area is seemingly flat, but beneath the earth lies an incredible story of destruction and beauty, and I find that to be truly fascinating. Thanks for watching.
Ballarat is a major regional city located in Victoria. It's one of the richest goldfields to have ever been discovered, but this area isn't actually as rich as it appears, and I'll explain why in this video. Ballarat is deceiving in many ways, and this deception cast by this ancient landscape has led to the city surviving and prospering when really it should have died when the gold ran out. But that's the thing, it never did. Because beneath the rivers that were hit so hard during the earliest days lay older rivers, buried deep, sometimes beneath dozens of meters of thick basaltic rock, and other times it lay up to 100 or so meters below it. So when these initial waterways were exhausted, the deep digging began. Tons of gold were pulled out of these ancient rivers, and then after much of this was exhausted, Ballarat faced a problem again. Now, around this time, when the gold that was mined from the present-day rivers got exhausted, Ballarat was more or less given two choices. Invest in exploring for more river gold, also known as alluvial gold, or resort to crushing quartz. In the late 1850s, hard rock machinery was primitive to say the least, with ore crushers being invented around this time for this purpose. The gold that hadn't yet been eroded by the eons that had passed since it was originally shot through the fractures within the earth in a molten state was still there, tied up within the quartz, with it sometimes being visibly tied up. And gold in quartz was visible everywhere around Ballarat around this time. In every place that wasn't covered over by a basaltic lava flow, more or less lay a gold-rich quartz vein, outcropping on the surface in a very proud and pronounced stance, due to the fact that it was more erosion resistant than the surrounding sediment, and often quartz veins would be interlain with rich amounts of very visible gold, sometimes shot all throughout the many fractures that existed. And this is where Ballarat gets a little cheeky. The early towns to start crushing did so because the quartz veins that were mined paid an amount that was more than the operating costs of the mine. But this type of mining was stupidly expensive. Many different machines were required, and large amounts of capital was often necessary for one of these companies to even have a chance of getting off the ground. So it had to be a damn good bit of gold-rich quartz for them to actually be able to profitably mine this. But in Ballarat, the quartz was shit. Seriously, it was absolutely trash in its yield. Most companies back then tried to get an ounce per ton at the very least around this time. But in Ballarat, the quartz barely gave 4 grams to the ton. This is just an average, and in rare occurrences it was more. But in general, Ballarat has some pretty shit quartz. So why the heck was there so much gold that had been eroded from the quartz here? And why is the amount so pronounced in Ballarat compared to the surrounding goldfields, which have quartz veins that have a much higher ratio of gold per ton than what's found in Ballarat? Well, it has to do with the height it's at. That's right, the height. Because Ballarat is more or less the top of the dividing range in this part of Victoria, and as a result of that, it's eroded much more than the surrounding topographically lower lands, meaning more gold has been deposited here as a result of more quartz being worn down to a particle size and releasing the gold that was interlain within it. And because of this, things got tricky, because quartz was everywhere, but you had to crush tons upon tons for it to even have a chance of being profitable. And that was almost impossible to do at this time in the late 1850s. So Ballarat saw an incredible amount of companies go bust in a decade that followed. Many people lost their entire fortune, and many others got swindled when people would offer false promises to investors, or make falsified discoveries, where they'd lie about the yield per ton. But amongst all the trash, a few companies learned to work around and even to benefit off the low-yield quartz that existed in Ballarat. The Black Hill Mining Company is one such example of a groundbreaking and extremely profitable mine that operated here for 40 years, and during that time it tore the mountain here asunder, creating an entirely new valley within it, as they bulk crushed an incredible amount of ore, and utilised a very smart and money-efficient way of transporting it, utilising a hard rock miner's best, or worst friend, if they fall down their shaft: gravity. But in general, if you're a small-time prospector, I'd advise you to not waste your time looking for hard rock ore here if you actually want to make a buck. But then again,
I could just be fucking with ya to keep all the quartz to myself. Nah, I'm just joking. Or am I? Yeah, I am. There's a great book about this called The Astonishing History of Ballarat, Volume 3, and it actually mentioned the amount of quartz that was necessary to be eroded to release the amount of gold that was found in the alluvial days of Ballarat. And it touches on the difficulties of setting up a hard rock mine here in the 1850s onwards, and the many challenges and successes that occurred in the spectacular goldfields of Victoria. And I highly recommend it. Thanks for watching. Antarctica is one of the few places left on our planet where vast deposits of untapped mineral wealth lies in abundance. It was, after all, merged with the southern parts of Australia for over 1 billion years. And as a result of this, the very same tectonic events that led to the geological construction and mineral enrichment of areas such as Victoria and New South Wales also impacted Antarctica and did the very same there. It was more closely tied to Victoria than to New South Wales though, so the same tectonic events that Victoria experienced, which led to it having some of the richest goldfields on our planet, also affected Antarctica, and this video is going to discuss why this frozen wasteland is hiding some of the largest reserves of not only gold, but of numerous differing valuable minerals, and how this could set the scene in the future for some of the largest conflicts between countries to occur, as they vie for dominance over the exceptional riches that lie here. Now, before we begin, I've gotten comments by many people telling me they'd like to help support the channel. So if you've ever considered it, I've finally opened up a PayPal donate button, and the link to donate to that will be down in the description below. In time, I'll also open up a Patreon, and I'll start with YouTube memberships as well. I work a full-time job that I'd love to scale the hours back on so that I can focus more on this channel. So any contributions would be beyond appreciated. Now let's get back into the video. As ice caps all around the world slowly melt, Antarctica is no exception, and as a result, it's changing rapidly. The Environmental Protocol bans all mineral resource activities in Antarctica, other than for scientific research in present day. This might be all well and good for now, whilst minerals are easily accessible in other countries, but in 100 years, when easy to find mineral deposits become exhausted and increasingly harder to find, I suspect attention will slowly turn towards two places: Antarctica and Greenland. I'll save my theories on Greenland for another video, but Antarctica is an incredibly ancient continent. It's gone through numerous cycles of tectonic collision and rifting. Mountain ranges have been thrust up, then fully eroded time and time again throughout the ages. When mountains get built, something truly special occurs alongside it: gold. Well, not just gold, other valuable minerals too, but gold is arguably amongst the most highly sought after. The region of Antarctica that interests me the most though is the section that was connected with Victoria. Most people probably don't realise that Antarctica and the southern parts of Australia have been connected for over 1 billion years before they finally separated as a result of immense tectonic rifting that began 85 million years ago, and the two continents were fully separated by around 30 million years ago. In present day, you can clearly see the faults in southern Victoria that were created as a result of this rifting here. Both Victoria and parts of Antarctica were an ancient seafloor 550 million years ago. Tectonic collisions occurred here numerous times as the ancient Paleo-Pacific Ocean subducted beneath this area time and time again, effectively thrusting up the ancient seafloor and crumpling and buckling it as massive mountain building events took place. These events stretched from the top of modern-day Queensland and went all the way down south past Victoria into Antarctica, raising the land from north to south above the ocean piece by piece, and depositing immense mineral wealth along with it. This vast mineral deposition would occur time and time again as numerous tectonic collisions occurred over the next 200 million years, and multiple mountain building events would take place. And along with these events were the filling of the many faults that were created in the bedrock during the immense buckling and uplift that was experienced time and time again here, with highly pressurized gold-rich fluids shooting up through these fractures and solidifying within the faults and cracks within the rocks, appearing today as quartz veins. So the same rocks that gold was literally sweat out of during metamorphism existed here in Antarctica too, as the two places underwent the same tectonic events, and therefore the goldfields in Victoria and those in Antarctica are more related than most people think. The source rock that fueled the massive gold enrichment of Victoria is thought to be Cambrian underwater basaltic volcanics. It's thought that when these rocks were subducted, the gold that was sweat out of this volcanic material directly led to the vast gold enrichment of places such as Ballarat and the entire Golden Triangle in general. But this is not including the goldfields of the Far East, which have a different origin. So essentially what this means is that in Antarctica right now is an area that mimics Victoria, which is mind-boggling to think about. In Victoria, massive, and I really do mean massive gold nuggets were found. Some of the largest in the world occurred here. I'm talking real freak-sized stuff. There's a very good chance Antarctica has this too. Both of these continents were relatively stable for hundreds of millions of years after the gold events took place until the rifting here occurred, which means the alluvial wealth held in the frozen over creeks and rivers in Antarctica would be truly unbelievable and unimaginable. It would be just like Victoria was in the 1850s. Gold everywhere. I can't lie, my dream that I'll never get to experience is to just dig a few holes in an exposed creek in Antarctica and do a few test pans. But I guess that experience will probably be reserved for whatever country wins the war over the resources that will inevitably occur here at some point in time in the next couple of 100 years. Assuming, of course, that we make it that far. So this is the truly astonishing story of Antarctica's link with Australia in more ways than one. From a billion-year-plus relationship between the two, to the vast mineral wealth that is contained within both continents. Australia and Antarctica are old partners that, for whatever reason, just drifted apart in time. I'm sure we've all experienced something like this in our lives, and we can probably relate to that. Maybe they'll get back together one day, and it'll be like a happy reunion. Or maybe the continents will find new, geological partners to play collision and mountain building with. Thanks for watching.
The story that we are going to discuss today is one that is over 500 million years old in its age. It's a story about a violent tectonic collision that produced a slew of positive and negative events. It built the landmass of eastern Victoria and raised it from the deep ocean, but it also led to the formation of extremely powerful volcanoes, accompanied, of course, by massive earthquakes and a tsunami risk. But it also deposited vast mineral wealth. That's right, this is also a story about treasure. These same destructive events released a slew of metalliferous wealth, a byproduct of the voluminous amount of magma that would upwell towards the surface during tectonic collisions. Valuable riches in the form of gold, silver, copper, and more lie in wait, stored in huge reserves, just waiting to be tapped into and found. But these riches were hidden so well, we never even knew they existed until very recently, when their existence finally came to light with the help of modern technology, which shed light on the existence of an ancient volcanic arc that still exists in present day, known as the Staveley Arc. And it's literally lying in an area that is now the relatively flat inland region of Western Victoria. This ancient arc was hidden beneath hundreds of meters worth of sedimentary material that had accumulated and buried it over many tens of millions of years. There are some places where the material associated with these ancient explosive volcanoes are exposed in present day, but these places remain few and far between, only further adding to the mystery that had stumped Australian geologists for decades, all the way back to the days of the gold rushes in the 1850s, when geologists were everywhere and mining was an incredibly important part of everyday life. But now technology allows us to peer beneath the surface, and this is what this video is all about. This is the story of Australia's brand new mineral rush, and the massive tectonic and volcanic origin that produced it. Gold, silver, copper, lead, these are just a few of the metals that lie in massive, and I mean massive quantities, and they are just beneath the earth, right now, just waiting to be found and extracted.
Volcanic arcs are associated with some of the most violent and powerful volcanic eruptions on Earth. The volcanoes that develop here are either your typical conical formation, known as a stratovolcano, which releases eruptions that are incredibly dangerous to be around, Or they can go one or more steps higher in their level of power, creating an eruption so strong it blows a stratovolcano apart and then collapses it to form gigantic calderas during the volcanic eruption, with some of these volcanic complexes being so powerful that they erupt at a supervolcanic scale, forming a caldera so large you most likely wouldn't even know you're in a caldera. Either version of these volcanoes can be so powerful that they can totally bury entire cities beneath tens to hundreds of meters worth of material in a mere matter of minutes, when they release giant pyroclastic flows or trigger violent lahars. These volcanoes are also associated with the formation of tsunami waves, occurring usually when a volcanic landslide occurs, or if the volcano is located near a large body of water during a caldera collapse. So when these arcs are active, it's a pretty turbulent area to be near. Along with the volcanic risk, you also have to deal with extremely powerful and frequent earthquakes and subsequent tsunami risks. But along with this danger exists valuable riches just waiting to be found. These arcs are associated with the release of extremely precious metals, with gold, silver, lead, and copper being a few of the metals that occur en masse when these events occur. And these deposits usually accumulate for millions or tens of millions of years, leaving layer after layer of extremely metal-enriched deposits that would make you rich overnight. But in order to find these, you have to know the different ways that these valuable and much sought-after metals accumulate, and we will cover all of this later on.
A volcanic arc is also known as a magmatic arc, and this giant belt of volcanoes form above a tectonic plate when another plate collides and subsequently subducts beneath it. Present-day examples of these types of volcanic arcs can be found within the Japanese archipelago, the Sunda Arc in Indonesia, or within the Andes. The volcanic arc we are going to cover today formed in exactly the same way as all of these examples, but it was more closely related to the Andes in the chemistry of its magma and in the topography of the land, meaning the place it occurred at more closely resembles the Andes in its biomes and overall layout, with gigantic mountain ranges stretching high into the sky, with hundreds of massive volcanoes and volcanic calderas dotted everywhere throughout the land. Victoria is located in the southeastern portion of Australia. It's known for containing some of the richest goldfields to exist on our planet, and the geology here is convoluted, layered, and beyond complicated. The massive sequence of effusive eruptions produced wave after wave of lava flows, and occurred at over 400 different locations all throughout the state, starting sometime around 2 million years ago, as Victoria drifted north over a hotspot that had been causing inland volcanic eruptions to occur in Australia since northern Queensland first drifted over it, and in time, the hotspot slowly moved south all the way to Victoria and beyond, lying somewhere beneath the Bering Strait in present day. The vast majority of the state is covered in basalt or is located beneath large amounts of sedimentary material, meaning vast amounts of wealth lie beneath the soil. But the only way to find and extract it is by understanding how this complicated geological puzzle that is Victoria formed, so that we can extrapolate this understanding towards deciphering what riches lie in wait to be discovered. The only issue is Victoria is unbelievably complex. Like really, it's an absolute mind. It's only recently that it's begun to be understood, purely because of modern day technology and the ability to measure deep within the Earth. As a result of this new ability, Victoria has some of the highest quality magnetic and gravity data available in the world from the recent and thorough in-depth studies that have taken place here. Magnetics allow us to peer down to about 30 kilometers beneath the surface of the Earth, and with gravity, you can see even deeper than this. And this data, combined with drill cores, can penetrate deep into the earth to take a sample of the rocks and investigate what minerals make up the layers without having to physically investigate it by constructing a mine shaft like they would back in the old days. And this unlocks the ability to prospect on an entirely new scale. So these techniques, along with other recent technology, have finally begun to unravel the complicated puzzle that is Victoria, and that has led to some truly monumental discoveries. Take this gold mine for example. It was discovered in an area where gold was first discovered in 1894, and it was then mined until 1903. But the old miners, who were amazing at what they did by the way, completely missed this unbelievably gold-enriched location. But how? Well, it was located beneath basalt that was erupted from the more recent volcanic eruptions, and was only discovered using modern techniques. It was completely hidden from the miners, and they had no way of knowing it existed there. But at only 15 meters beneath the surface, underneath this basalt, lay a vein of quartz so gold enriched that it yields 1429 grams per ton, which is unbelievable. That means this mine earns 115,277 Australian dollars per ton of ore crushed, and they've mined over 3.5 million ounces of gold since the commencement of the current operation in 2015. This is one example of what recent technology is allowing us to discover, and the next discovery might be a Fosterville times 1000 or more, because this isn't just one spot that's been discovered. It has unlocked the potential for an unbelievably vast amount of mineral wealth located underneath a vast stretch of land. And this is where our story drifts back to the magmatic arc. Victoria formed within the past 550 million years. It was originally just a deep ocean that lay off the east coast of Gondwana. Tectonic collision occurred as the ancient Paleo-Pacific tectonic plate collided with the continental plate of Gondwanaland, and the heavy oceanic Paleo-Pacific plate subducted beneath the lighter continental plate. This collision led to the formation of a gigantic volcanic arc, known today as the Staveley Arc. It stretched from the shores of ancient Gondwanaland, which is now in western Victoria, all the way south and into Antarctica, which at this point in time was connected to Victoria, so a good part of this volcanic arc is also located somewhere in present-day Antarctica too. This entire magmatic arc lay hidden from the naked eye, and was completely undetected as it sat buried beneath vast layers of sedimentary material which had buried it in the past 500 million years since it finally became extinct. But when you look at it through the magnetics, suddenly something amazing pops up. As you can see, this completely changes our ability to see things. Suddenly, the large stretch of sedimentary plains and desert have become invisible, and what we now see are the remains of the now dead volcanic arc that roared to life vigorously 511 million years ago, but that most likely originally began life around 522 million years ago. This volcanic arc has changed dramatically though. It looks nothing like it would have when it existed. There have been several tectonic events that occurred here post 500 million years ago, and these collisions have folded, buckled, warped, and moved the volcanic arc all over the place. The orogeny that caused this buckling is most likely what killed the volcanic system to begin with, by thickening the crust and choking off the ability for magma to easily rise. And the multiple orogenies that would occur would lead to 19 present-day belts that exist of both volcanic and intrusive rocks. But 500 million years ago, they would have existed as only 4 large volcanic belts, before becoming twisted and rotated along with the present-day marvel known as the Grampians. 440 million years ago, the deep ocean retreated eastwards, and mountains began to be built, raising another large portion of Victoria out of the deep ocean. And it was during this time that the Grampian strata was laid down, burying the rocks that made up the Staveley magmatic arc, before becoming tilted and folded 405 million years ago, in an event that also affected the much older rocks that made up the Staveley magmatic arc. After this event, this part of the Earth became so stable that it preserved the upper crustal levels of these 500 million year old rocks, leading to them existing in present day, rather than them having been exposed and eroded away. This is extremely unique and is quite a special occurrence. So the reason why this discovery of the Staveley Arc is so significant, among many other reasons, is because the Andes are known for having some of the richest copper porphyry deposits in the world. And along with that, the Andes also has vast quantities of other valuable metals such as gold. It is a place of immense tectonic activity in the form of earthquakes, and there exists some of the strongest and most explosive volcanoes along the entire Andean mountain range, from your standard Plinian volcano all the way up to supervolcanoes that are active in present day. So 500 million years ago, if you were to stand at this location and look out to the east, you would see nothing but a vast stretch of ocean that would be the Paleo-Pacific Ocean. And if you looked west, you would see massive rugged mountains similar to the Andes, only located in present-day Victoria. The one difference is that the Andes is tectonically active in present day, whereas this volcanic arc is long dead. This is huge because the most valuable phase of mineral injection is in the final pulses that are released by the magmatic system as it is about to die. This final burst of fluidic wealth deposits the largest and the most richest layer of gold, silver, copper, lead, tin, etc. The reason this occurs is because as subduction ends, it's changed from the arc being shortened and squashed to suddenly being released into extension again. The final release of this confining pressure results in a massive pulse of magmatism that brings metalliferous granite and porphyries towards the surface. So somewhere underneath the deserts and sedimentary plains of Australia lies an incredible amount of vast mineral wealth that might be worth billions upon billions of dollars or more in value. And these riches lay not only in the volcanic rock that was released, but also in the much wider stretch of land, with nearby sedimentary rocks from this date, 500 million years ago, also containing vast amounts of these riches. But how could sedimentary rocks contain them? And how do bursts of pure gold and other valuable metal deposits form? One way is within what is known as volcanic massive sulfide deposits, or VHMS deposits for short. These form directly on the seafloor in an area where ocean crust is being stretched away from the subduction zone. When highly active, these deposits can be associated with what is known as a black smoker environment, which are essentially chimneys located directly on the ocean floor that are constructed out of valuable metals that increasingly accumulate with time as more acidic fluid continues to upwell through the ocean crust. When the Paleo-Pacific Ocean was subducting beneath Australia, the section that was magmatic occurred mostly in the oceans near the continental land of Gondwana. It started deep within the ocean and released wave after wave of VHMS deposits during its life. Black smoker environments scatter precious metals all over the place, leading to them accumulating on nearby sedimentary material, where it would then become intertwined within it. So the area of land that could be enriched is vast beyond words, and these metals all tend to accumulate with other metals of the same type because of their varying specific gravity. So when one section is discovered, vast amounts of it lie in one area, making it easier to extract. But there's a second way that these valuable metals are deposited, and that occurs with a phenomenon known as porphyry deposits, which itself includes epithermal deposits. Porphyry deposits are the final burst that I mentioned earlier. They are intrusive deposits and they form at depths of 1 to 6 kilometers beneath the surface. As magma cools, metals begin to precipitate out of the highly pressurized and hot hydrothermal fluids, and they begin to enrich the nearby rocks around the magma chamber, creating what can only be described as a mineral-rich halo around a slowly cooling and solidifying magma chamber. As temperatures drop, metals begin to separate out one at a time, beginning with copper, followed by molybdenum and gold, then silver, lead, and zinc. creating zonations of enriched areas with different metals. As the magma chamber cools, the top of it crystallizes, resulting in the release of water and other volatiles. These hydrothermal fluids carry metals from the top and exterior of the magma chamber into the surrounding rocks as it exploits cracks and voids above it. As these metal-rich brines ascend and the pressure decreases, they eventually reach their boiling point, at which time metals begin to drop out of solution. Again, like before, copper comes first, followed by molybdenum and gold, then silver, lead and zinc, as we get further away from the heat source. This process creates epithermal deposits above the magma chamber, which form in the cracks in the surrounding rock as veins and along weak sedimentary plains as sills, which can then be exposed due to erosion or can still remain preserved. In this case, they are preserved and they lay out there right now, hidden beneath the sedimentary basins of the Murray and Otway Basin. So this final porphyry phase occurred at the 500 million year mark, when this volcanic system released its final metal-rich pulse of metalliferous porphyry deposits and granites that intruded into the upturned fault slices of the dying Staveley Arc, with epithermal and VHMS deposits located across an incredible stretch of flat, ordinary, and deceivingly boring land, with sedimentary rocks also containing it, which only further increases the search radius, meaning there's not only a brand new gold rush that's about to occur at a modern day level in Victoria, but there's also a potential for a copper rush among other metals, with billions upon billions of dollars in rock form laying out there right now just waiting to be claimed. It's just been discovered, so it won't be long until the riches that are lying out there in wait are found and extracted. So in present day, the fault known as the Moistened Fault marks the line where the ancient continent of Gondwanaland met the subducting Paleo-Pacific tectonic plate, which is something that I find fascinating, and this is why I love geology. This entire story is just incredible in my eyes, and the riches it left behind to be claimed are just mind-blowing to me. It astonishes me to think that at this point 500 million years ago, to my west was the vast supercontinent of Gondwanaland, and to the east was a vast ocean that stretched out for hundreds to thousands of kilometers into the distance, and right at the edge of the continental plate lay a vast chain of explosive volcanoes that would lay down vast mineral wealth, and whose image still exists to be seen in present day with magnetics. This is the closest I can get to a stratovolcano in my home state, and I'll take it.
I'm standing in an area of land known as the Pyrenees, and this road cutting here has revealed some truly spectacular rock formations. These bulbous rocks here look almost alien, and the bands of varying depositional proportions throughout this one are truly gorgeous to say the least. The mineral enriched quartz that has been shot through the bedrock here around 440 million years ago is my favourite though. The beautiful colours and shapes is just, I can't even explain how beautiful I find these rock formations. I could literally spend hours staring at this cutting. When erosion works to whittle down the sedimentary material surrounding the erosion-resistant quartz reefs, it reveals these strange looking shapes, and each of them feature their own unique style of appearance. The composition of minerals featured within these reefs are all different. Some are more abundant in certain minerals, and others less. Some are stained in iron, and others feature rich colours from blacks, purples, oranges, and more. Some carry gold, and others are devoid of it. I've driven past this cutting numerous times, but this was the first time that I've stopped and properly investigated it. And honestly, I was blown away. There's so much going on here, and there's so much unique beauty to be witnessed in this one single spot. So let's all take a moment out of our busy, stressful lives to appreciate the beauty afforded to us by this immaculate planet of ours, by taking in the spectacular appearance of these ancient rocks. These rocks here are some of the oldest in Victoria. They were laid down during the Middle Cambrian period some 510 million years ago, and the sedimentation continued through until the early Ordovician, with it ending around the 482 million year mark. The origin of these rocks is derived from the erosion of a relatively new landmass that was slowly being thrust out of the deep ocean to the west of here. And the tectonic collision that was responsible for this formed a massive volcanic arc known as the Staveley Arc. This arc began its life around 530 million years ago, and the Moisten Fault marks the location where the ancient subduction event that created this volcanic arc occurred. As this arc and the land around it began to be uplifted out of the deep sea, the sedimentation that formed the Pyrenees strata that we see here began. Much of it seems to have been derived from the erosion of the newly forming landmass that was uplifting mighty mountain ranges to the west, with additional sediment most likely coming from Antarctica too, which was located in a snug position to our south. And that's where the rocks from this road cutting begin their story, building up as sedimentary deposits layer by layer in a deep sea environment before proceeding tectonic collisions eventually uplifted this stretch of the ocean, in the very same way that the land to the west of it was uplifted, by chaotic tectonic collisions that would entail numerous subduction events and even a continent-to-continent collision too. These tectonic collisions folded, buckled, crumpled and tilted the rock layers from being horizontal to being almost completely vertical in their orientation, as the land was squeezed from east to west by the many tectonic events that would occur here between a 440 to 360 million year mark. But one last thing would occur to these rocks before this land would become more or less geologically stable, and that would be the intrusion of a massive magma chamber which occurred here around 360 million years ago. This massive churning magma chamber cooked these rocks, leading to additional metamorphic changes that would see them transformed into hornfels. A hornfel, simply put, is when rocks are metamorphosed by high heat but low pressure, and this occurs when rocks make contact with a nearby intruding magma chamber or from friction-related processes that are inflicted to a strata by tectonic-related processes. In this case, it was metamorphosed from a nearby magmatic intrusion, and this intrusion of felsic magma never got a chance to erupt. Instead, it cooled and solidified beneath the Earth. Now that we have the geological context down, we can begin to get an idea of why these rocks look the way they do. Any quartz that you see here wasn't originally laid down in a deep sea. They intruded into these rocks much later, where they would be shot up from deep within the Earth, through the many faults and fractures that were created en masse in the bedrock during the tectonic collisions in a fluidic state, only to solidify into these beautiful quartz reefs once a drop in pressure and temperature allowed them to do so. They are a byproduct of the subduction event, and they were originally deposited deep within the Earth, meaning many kilometers of erosion has occurred since they were shot through the bedrock to reveal them to begin with, showing just how much of this land has been eroded down through the eons, as this entire landscape featured a major mountain range that once stretched many kilometers high up into the sky. But in present day, it was little more than small, rounded, hilly stubs, a shadow of its former self. You can see this is a strata dominated by sandstone and mudstone that were carried here by turbidity currents from the west, which are essentially major underwater landslides that occur on the edge of a continental shelf, which are responsible for propelling sediment for tens to hundreds of kilometers into the deepest part of the sea, known as the abyssal plain. And this land was once that abyssal plain. Upon looking around and reading the rocks, it became evident that a river once flowed over this area too, and I can find some nice rounded rocks around here that provide that information. This area that I'm standing in is actually the last to feature a surface outcrop of this ancient Cambrian age Pyrenees strata, because as we head further west, the land becomes dominated and smothered by recent lava flows in a prolific manner. At least 50 meters or 164 feet worth of basalt dominates most of the land from here onwards. As you can see, the basaltic eruptions have formed a major plateau, and this is actually a great example of the type of land that Ballarat was built on. I'll try to make a separate video on this, but this area here, where the basalt rises, is literally the type of land the western part of the town was built on. Now, obviously, the basalt didn't just decide to stop here. In both cases, it went beyond this point, but the nearby rivers wore it down, and the Yarrowee in Ballarat did much of the same. So I hope you enjoyed viewing these beautiful rocks as much as I did. The Pyrenees strata is one of the oldest rock units in Victoria, and even though the Pyrenees have been highly eroded, It's very evident, even in present day, that it was once a remarkably tall mountain range. Now, before we end this video, I just want to give a big shout out to these pieces of carbonate rock that I randomly found on the roadside when I was shooting footage of the volcano here. This was stupidly cool to see, and totally unexpected. This is a great example of the oceanic origin of this land, and it takes us back to a time when this area was a shallow sea, and coral reefs were able to dominate the land. It appears that this basalt has smothered some of these coral reefs, which appear to have once outcropped here, or it was possibly exploded out by a volcanic eruption from deeper within the earth. But I think it's the former rather than the latter. The Great Dividing Range is a truly spectacular mountain range. It stretches from Queensland all the way through New South Wales down into Victoria, where it then curves west and stretches up to and past Ballarat. And even though it's pretty unrelated to the Great Dividing Range, at least geologically and tectonically speaking, the Grampians is more or less where the line is drawn as being the end of the range. But why does a relatively tectonically stable continent have this mountain range? Australia is smack bang in the middle of a tectonic plate, meaning there are no nearby tectonic collisions occurring, which is what builds these mountain ranges to begin with. And in Victoria, the Alps are actually still rising, and according to John Engel and Professor Woodhead from the University of Melbourne, the eastern highlands of Victoria have been steadily growing at a rate of 76 metres every million years, and are still growing to this day. And the reason for this is related to New Zealand. But why does it curve when it hits Victoria? And what's the deal with it stretching west, going past Ballarat, and ending far into the state? Well, this part of the story has to do with an ancient mountain range that exists here and its relationship to Antarctica. This is a fascinating story. I'm going to try to keep this video as short and engaging as possible. I might simplify some things, but I will try to not omit too much as I describe what is currently happening with the mountains and fault systems that underlie them in eastern Australia. By the end of this video, you'll understand why Australia contains the third longest land-based mountain range in the world. The start of the Great Dividing Range can more or less be placed at the beginning of the breakup of Gondwana, which was a supercontinent that would form around 550 million years ago. It would remain this way for over 300 million years, with the landmass of Gondwana beginning its split around 180 million years ago. This split led to the formation of the Great Dividing Range. To the east of Australia, Zealandia began to rip apart from Australia, spurred forth by massive pulses of basaltic magma that penetrated into the many faults and weaknesses created by the rifting, and began to push its way up with wave after wave of volcanic eruption occurring. This was the beginning of the Tasman Sea, and New Zealand would continue west furthermore. This rift zone created enormous tension to the plates east and west of it. It squeezed, buckled, fractured and uplifted them, pushing the deep ocean sedimentary material that made up the bedrock of eastern Australia and the massive amount of volcanic rocks that existed alongside it upwards into the mountain range we know today. This would continue until the rift zone eventually became sealed shut forever, and suddenly this was the end. And really, this should have been the end for the Great Dividing Range if it wasn't for New Zealand undergoing incredible tectonic events. The Dividing Range could have been nothing more than tiny bulbous hills due to the erosion. But it isn't. Instead, the subduction event occurring in the North Island and the continental collision between the Indo-Australian and Pacific tectonic plates that is occurring and making up the majority of the South Island, along with yet another subduction zone occurring even more south to this, led to the preservation and continued uplift of the Great Dividing Range. If you watched my video on Victoria's most recent earthquake, you'd know that compressive stresses that are occurring in New Zealand are indeed being transferred through the crust, beneath the Tasman Sea, all the way to Victoria and beyond. The Earth is interconnected far more than people realise, and this connection has luckily led to the formation of a spectacular mountain range in a geologically stable continent like Australia. Compressive stresses transferred through bedrock pushed up the many thousands of faults that exist in eastern Australia when Zealandia broke away from us. These faults became uplifted, and this uplift is the mountains we see today. After the rift zone in the Tasman died out, the tectonic collisions that modern-day New Zealand is facing, which I suspect were the reasons the Tasman rift zone died out to begin with, are the reason the Great Dividing Range still exists today, and is still growing with each passing year. Moving on now, in Victoria, we have this curve. Why? This is the most fascinating part of the story, for me at least, because the knowledge of it is to some extent new. Victoria was always mountainous, and it was like this many millions of years before the Great Dividing Range began life. Victoria's far west was once as high as the Andes, with the ancient Paleo-Pacific Ocean stretching as far as the eye could see. If you were standing on the Grampians, which actually didn't exist 550 million years ago when Victoria first began its life and transition from a deep sea to a mountainous, uplifted land, all you'd see was the ancient Paleo-Pacific Ocean in front of you, and behind you would have been massive, uplifted, volcanically dominated Andean-style mountain ranges. We had one tectonic collision that occurred after another, and these collisions slowly assembled both Eastern Australia, but more specifically Victoria bit by bit. And with each new section that was added, a new episode of mountain building would more or less accompany it, minus the odd minor rift event here or there. In the east, the Victorian Alps are definitely influenced by New Zealand's compressive stresses, and that's why the mountains there are pretty spectacular. But the Great Dividing Range stretches past Melbourne into an area known as the Central Highlands. This area is the ancient remnant of the original mountains that occurred here, only it's been pushed up recently again, and I'll get into why in a moment. So these original mountains have been heavily eroded in the 450 or so million years since they began life. They're small bulbous hills that are several kilometres lower than what they once were due to erosion, but they also got a breath of fresh air, so to speak, or a second wind, along with the Great Dividing Range. I'm not entirely sure just how affected this area is by New Zealand's compressive stresses. I'd say it definitely has some part to play, but it was only quite recently realised within the past few decades that Victoria had a major north to northeast faulting attributed to it, which was quite surprising, because originally it was believed the faulting was only east to west in nature, minus a few anomalies here and there. But like Zealandia, Antarctica also said goodbye to Australia when Gondwana broke apart, and the rift event that occurred never stopped. In the present day, you can clearly see the rift zone here. Magma continues to rise from the crust to fill the weaknesses this rift is creating, and this magma is pushing Australia and Antarctica apart ever more. The compressive stress generated by this pushing is still being transferred into both continents. When this event originally occurred, the Otways was formed. The Otways have mountains that are quite different to Ballarat. They are bulbous, but spectacular in size, and they're still growing as well. And beyond them, the compressive stresses are being transferred all over Victoria in a north to northeasterly direction. These stresses are pushing the Central Highlands up. So this is the incredible story of Australia's unique geographical landscape. What a truly spectacular land this is. Australia is fortunate in that it's located in a perfect position within the Indo-Australian tectonic plate, to protect it from many of the extremely dangerous natural disasters that places such as the US or Indo-Asia face. Events such as major earthquakes, tsunamis, or the more larger, dangerous volcanic eruptions released by subduction-related volcanoes such as Mount St. Helens or Krakatoa don't occur here. And yet the last time a volcano erupted was within the past 5,000 years in South Australia. And this volcanic eruption was definitely dangerous, as it was quite an explosive event, albeit to a different degree than the volcanoes that I just mentioned a moment ago are. What's even more amazing is when you learn that this isn't some random occurrence. Australia has been volcanically active for the past 31 million years, give or take. But why? And if it's volcanically active, why is barely anything known or spoken about regarding our volcanoes?
As a person who grew up in the Australian education system, I can honestly say I can't remember Australia's volcanism or even the word volcano being mentioned in my late high school years, which scores a 0 out of 10 in my books. At least teachers in primary school got us to make a papier-mâché volcano. The craziest thing is the very place I grew up had a feature that I used to ride my bike near as a kid all the time without even realizing it was a volcano. And the entire landscape was basically one rock and one rock alone. Basalt. All I saw, basalt. Basalt here, basalt there. And then when I went to the goldfields and saw quartz for the first time, my child mind was blown. Anyway, the fact is, Australia has been completely altered by these volcanic eruptions. They stretch from the northern part of Queensland, beginning 31 or so million years ago, all the way down to Victoria, and now beyond it, with volcanic eruptions likely to begin in Tasmania in the next few million years. So in this video, we're going to take a look at how Australia, a seemingly tectonically stable country, could experience the scale of volcanic eruptions that it has in recent history. Held belief to explain Australia's volcanism was that the tectonic plate, which is slowly moving north and is on a collision course of Indonesia, drifted over a mantle plume, which is a mass of hot, buoyant rock that is upwelling en masse, releasing tremendous amounts of voluminous basaltic magma that is seemingly inexhaustible. This is definitely still partly true to some degree. Australia is definitely drifting over something that is static, and the way we know this is that volcanic eruptions have been steadily moving south as Australia drifted increasingly north. But recently, the long-standing theory that tried to explain the origin of these volcanoes was shown to either be incorrect or missing some crucial detail. There's two names to describe the hotspots fueling these eruptions. Some scientists think it was more than one hotspot, whilst others think both are one and the same. Personally, I've always used these names interchangeably, as I personally think it's only one major hotspot that exists beneath us. The first is the Cosgrove hotspot, and the second is the East Australia hotspot. The problem is, recent in-depth ground scans that mapped this plume revealed it to have a shallow origin. This is bad, because our idea of mantle plumes are just that, they come from the mantle. This is more like a crust plume, and this has completely messed with our understanding of everything. Something strange is going on beneath Australia, and we aren't too sure what it is. We only have part of the picture, but it's definitely a plume of some sort, but it doesn't stretch deep in its origin. Regardless of what it is, the fact of the matter is that Australia has drifted over a hotspot. Hotspots are pretty common. We know about the one that makes up Hawaii, as the Hawaiian Islands themselves also drift over time. And if you look on Google Maps, you can see the eroded older versions of their ancient self as they continue to move ever more. Yellowstone in the US is another example of a hotspot, as the location of this plume has slowly changed over time, as the US has continued to drift. The volcanoes in Australia released a mixture of effusive and violent explosive eruptions as they moved south. In Queensland, we have intrusives and the remnants of major basaltic lava flows, along with felsic and intermediate volcanic eruptions that released andesite and rhyolite and were very explosive and quite dangerous to be around. Many incredible volcanic sites, like the Undara lava tube, were created by this hotspot and the recent eruptions. But along with this, we also have alkaline magma being released. This can happen in some other events, such as ocean island volcanism and in continental rift valleys, but they are a signature trademark of hotspots, as they release this magma quite readily, much more commonly than subduction-related volcanic arcs, which will typically only see this type of magmatic composition occurring in the back arc basin and away from the arc itself. In New South Wales, we had the same. Tweed Volcano was a mixture of effusive and explosive eruptions, as were many of the other volcanoes as we drift south ever more. We have widespread volcanic activity at Warrenheip and the Liverpool Range, to name a few. The Snowy Mountains were also fueled by this hotspot, and volcanic activity occurred around here too. Around 7 million years ago, it reached Victoria, and things kind of changed because the intensity ramped up. Not so much in terms of the explosivity, although there were many explosive volcanic eruptions, with a number of them leaving behind caldera lakes as a result of magma interacting with shallow groundwater and creating explosions, but more so in terms of the voluminous amount of lava that was released, which literally changed almost half the state, burying much of the older land beneath up to 60 meters worth of basalt in some areas. And there are well over 400 volcanoes in Victoria, some of them highly eroded, others are kind of meh, to the point of being unnoticeable or even unrecognizable as a volcano to begin with to the untrained eye, and others are actually pretty big. All you need to do is travel through the Creswick area to see some absolute beasts, like Mount Karuchiang. Volcanism here released massive amounts of effusive lava, and, like before, some of these eruptions were trachyte dominated, forming one of my favourite places in Victoria, Hanging Rock. The weird thing though is the fact that the only explosive volcanic activity that would occur in Victoria would only do so when basalt interacted with groundwater. So this begs the question, why are there no felsic explosive volcanoes in Victoria that were fueled by this hotspot like we had in New South Wales and Queensland? Well, my theory is that the magma was able to ascend without much issue, and as a result of this, much of the old volcanic rocks that Victoria is comprised of didn't have the same level of melt occur, as a result of the pronounced weaknesses and new fault lines created by the Horst and Graben events that occurred when Victoria separated from Antarctica, which created the first ever north to northwest faulting event in Victoria. And when I looked at the spatial distance between the volcanoes, I can't help but notice a pattern here, and it looks like the volcanic eruptions themselves are in a line and are erupting from the areas most affected by the Horst and Graben events, which is something that I'm very fascinated about, and I can't wait to show you guys some things that I've discovered relating to this. So, after passing through Victoria, the hotspot appears to be somewhere in the Bass Strait, and it's possible that it'll leave its legacy in Tasmania before finally slipping away from Australia's reach, where it will then go on to become an oceanic hotspot, and volcanic eruptions will appear on the ocean floor, as Australia continues its journey northward ever more. Thanks for watching.
This is Victoria. In 2021, a magnitude 5.9 earthquake occurred here.
I don't know what's happening.
This kind of earthquake is, well, weak in terms of global standards, but kind of surprising to have happen in this region, which is considered to be tectonically stable. And that's where our friends across the ocean enter the story, as, well, New Zealand is ultimately responsible for reactivating ancient fault systems in eastern Australia, and the story of how it does it is astonishing in a number of ways. So let's take a look at what's happening here. When the 2021 earthquake hit Victoria, it did cause some damage, mostly to the ego of the people who thought Australia wasn't tectonically active. But some buildings also kind of fell apart, and tall apartment buildings that went up to 50 stories high also shook pretty ferociously for like 20 seconds, and the people inside of them understandably freaked out. Also, one dude also had some construction stuff fall on him during the quake, and he sustained minor injuries. But I'm sure his mates bought him a beer after it, so it was probably all good. This earthquake reactivated an ancient fault line that was over 400 million years old, and that formed during one of the many uplift events that Victoria would undergo back when it was little more than a deep ocean. This fault is named the Governor Fault, and it's actually quite massive. It's a very large complex structure extending from the Murray River in northern Victoria down to around Gippsland Lakes in the south, passing directly through the Victorian Alps in the process. The fault is very deep too, with it being over 35 kilometers deep into the earth and likely extending much more than that. So this fault's quite old, and there's hundreds of other faults just like this one in Victoria, and if enough stress is applied, literally any one of them can reactivate. So across the ocean we have New Zealand. New Zealand is basically the ideal place to be if you're into earth sciences. We've got an incredible array of things going on here. First, the oceanic Pacific plate is subducting beneath the continental Australian plate in the eastern part of the North Island. Then it suddenly flips around and turns into a continental collision occurring in the South Island. This occurs because two pieces of continental crust can't normally subduct beneath one another, and so they grind against each other instead.
The New Zealand Alps are basically the mini version of the Himalayan mountains. After this, when we go further south, things get even more complicated when it decides to flip around, and now all of a sudden the Australian plate is subducting beneath the Pacific plate. It's basically like an earth science version of an extremely strange R-rated movie. Everything is going on here and no one gives a damn. But the thing about geology that a lot of people underestimate is just how much the Earth is interconnected, and how stress from geological processes get transferred even from places that are thousands of kilometers away. And in Victoria, this is exactly what is happening. The nearest tectonic activity to Victoria is over 2,000 kilometers away in New Zealand, where, as you already know, two continental tectonic plates have collided and are grinding against one another here, forming the massive New Zealand Alps in the process. The massive amount of compressive stress generated from this monumental mountain-building collision is being transferred west through the crust beneath the Tasman Sea and into Australia, creating these unusual earthquakes in Victoria, and basically forming the realization that Victoria's geological history and future is intimately tied with what is happening in New Zealand. And I find that to be incredibly fascinating to say the least. This has been happening for tens of millions of years, and will continue to do so for a very long time, and a 2021 earthquake was just a testament of this ancient process that's still very much alive in present day. Thanks for watching.
So I originally made a video that discussed how New Zealand is more or less responsible for the earthquake that rattled the state of Victoria in 2021.
I don't know what's happening.
The occurrence of this earthquake surprised a lot of people. Many Australians thought we were free from hazardous earthquakes because Australia is smack bang in the middle of a tectonic plate. But nope, this isn't true, as the transference of energy from nearby tectonic collisions gets transferred to distances both near and far from the point of said collision, and the activation of Australia's ancient fault lines is known as an intraplate earthquake. So in this video, we'll look at why these two recent earthquakes occurred, where they occurred, how they happened, what role New Zealand plays, and what we can expect in the future. The part of Australia that experienced these two recent earthquakes have the tectonic collision occurring in New Zealand to blame, as that's where the nearest tectonic collision is. There's just a filthy display of tectonic absurdity happening here. Look at this, we have a subduction zone here, a continent-to-continent collision, and another subduction zone. What the heck? But hey, I guess I can't complain because it created one of the most stunning places in the world. But still, I always look at this messed up tectonic scenario and just chuckle. So with subduction zones, the oceanic plate subducts under the continental plate. This is occurring in both the North and South Island, and again, laughably, they're pushing in opposing directions, which just further adds to the hilarity of this messed up tectonic situation. In the middle, we have a continent-to-continent collision. When two continents collide, subduction can't occur. Instead, the two plates grind against one another, indefinitely, producing spectacularly large mountain ranges. And unsurprisingly, this type of collision created New Zealand Alps. And the same kind of collision is responsible for constructing the Himalayan mountain range too. So there's a lot of compression occurring here, and the stresses from this compression gets transferred to distances amazingly far away from the site of the collision, utilising faults and fractures in the earth. And suppose you've watched any of my videos on Victoria, in that case you'd know this state was constructed piece by piece, starting from the west around the Grampians area and slowly moving east over time. Victoria was little more than a deep seafloor 500 million years ago, and numerous subduction events and one continent-to-continent collision that occurred when Tasmania collided with us 430 million years ago saw the construction of many major mountain ranges, from the Pyrenees to the mountains that were constructed in the Ballarat region and beyond. So the land beneath Victoria is highly fractured, faulted and buckled, and a slip of any of these faults will create an earthquake. So New Zealand's got a lot of stuff on its plate, pun intended, and the energy gets transferred through the highly fractured and now extinct rift zone that opened up the Tasman Sea, through into the faults in Victoria. As compression builds, these rocks slip and bam. Most of the time these earthquakes occur at a low magnitude, but there have been some exceptions. A significant magnitude 7 earthquake dammed the Murray River some 70,000 years ago. So big ones can occur, but they are rare, and it largely depends on the fault system, and whether it's a major or minor fault. But you get the idea. our land can still definitely shake. But let's look at the first one that occurred in a place I know well, and have spent much time in my distant past. The one in Sunbury, which happened on the 28th of May. This hit with an approximate magnitude of 4.1, occurring at a depth of roughly 8.6 kilometers, plus or minus 2 kilometers. This was weaker than the magnitude 5.9 Mansfield earthquake that I covered in a previous video. The link to that is in the description. This fault in Sunbury is particularly interesting to me. Why? Because it occurs right near the boundary of where the microcontinent of Van Dieland, which hosts Tasmania and goes all the way up to Melbourne and beyond, collided with ancient Victoria 430 million years ago, meaning this was a continent-to-continent collision. And you can clearly see that even today. The once mighty and significant mountains of the area that we call the Brisbane Ranges were constructed during this event, alongside the mountains to the east of Gisborne. And the predominant reason I find this compelling is that the only gold discovery ever made here that was exploited was in Sunbury. The location of said mine is directly above this fault, so it was most likely the conduit that was responsible for depositing the gold-bearing fluids in the bedrock here. The last time an earthquake occurred this close to the capital city of Melbourne was in 1932, when a similar one happened on the Mornington Peninsula. And it's worth noting that a significant fault in Mornington and another near Geelong has the potential to slip and induce a magnitude 7 or 7.5 earthquake. Such a thing would be unbelievably damaging, so thankfully they're sporadic. But along with the faults that we've identified are thousands of others that are yet to be. The earthquake that occurred in 2021 did so at a previously unknown fault line. We have a very complex geology in Victoria. The most recent earthquake occurred on the 5th of July in Pakenham. Unfortunately, I was asleep when this occurred, and I can't tell you how disappointed I am in myself. I've talked sternly to my circadian rhythm, and we've concluded that we can no longer allow ourselves to sleep lest we want to risk missing another one of the Earth's groove sessions. However, this was a minor groove, with the ground shaking at a measly magnitude of 2.1. Still, clearly, it was shallow enough to be felt and recorded by the general public. And when I checked the depth, it was at only 3 kilometers, so that would make sense. It appears to have been the Tankerton fault that ruptured. So to conclude, there's no need to panic, this is a natural thing. 30 to 40 earthquakes occur weekly in Victoria, New South Wales and Tasmania. The rest of Australia is seismically active too, in a similar fashion, with the transference of energy occurring in the north, and the west and south of Australia are no different. So this is a normal part of our land. We should be informed about it and take the necessary precautions to avoid damage and injury. Who am I kidding? We all know that it'll be ignored until a magnitude 7 rips through the city and causes untold damage, after which all the officials will act surprised, and introduce a whole new wave of laws to flip the construction industry entirely on its head to make new buildings earthquake-proof. And that's just the way it goes here, hey? Earthquakes are deeply entwined in the geological history of this land. It was only during earthquakes that the many gold-bearing fluids were released and shot into the fractures within the bedrock, solidifying into these beautiful outcrops of quartz that we see strewn everywhere. And if it wasn't for gold, Victoria and Australia would be a completely different place. Thanks for watching.